All right, so welcome everyone. Today I'll tell you a little bit about eigenvalue interlacing, definition, what it is, some theorems about eigenvalue interlacing, a general theorem which is called Courant-Hilbert theorem, which applies to real and symmetric matrices, also to Hermitian matrices, but we'll just do it for real and symmetric matrices. And then we'll see applications to graph theory via two methods, one which is called Cauchy interlacing and one which is Hemmer's interlacing. And if we have time at the end, I'll show you a couple of examples, and in the afternoon we'll do more examples related to these methods. Okay. So I'll start with the definition. So today we'll talk about eigenvalue interlacing. First, what is interlacing? Assume that we have two numbers m and n, natural numbers, and n is the larger one. Okay. And then we'll have two sequences: a longer sequence of length n and a smaller sequence of. Assume that let me see how I. Okay, so theta 1 greater or equal to theta 2 greater or equal to theta n is a sequence of, is a set, well, let's say sequence of real numbers. Assume that, so I have this one, and let me write it this way, and mu1 greater or equal to mu2 greater or equal to mu m are two, let's say, collections of real numbers. So again, maybe I'll put it this way, n greater or equal to m, so that we have more thetas than we have mu's. We say that the sequence the sequence mu1, mu-n, mu-m interlaces theta 1, theta n, if the following holds: if for every I from 1 to m, if I look at the if I look at the theta I entry in the big sequence, this is going to beat the corresponding I entry in the small sequence. But you have something which may seem a little bit weird. I'll show you an example in a second on the other side, and this is going to be greater or equal than theta I plus n minus m. So this is the general definition. Again, for us, these sequences are going to be eigenvalues of two matrices, but the definition is general. Anytime you have a sequence of real numbers, the sequence that have smaller number of members interlaces the other sequence if the numbers from the smaller sequence kind of go between the numbers of the bigger sequence. So let's do one example that hopefully will help you understand. Let me do it here. So let's see what happened in this definition if m equals n minus 1. Okay. Now, again, I will have, I hope this is not going to be too confusing. I have this sequence theta 1, theta n. Now I'm going to draw it on a line. And of course, if I draw it on the line, the order is the other way. So I have theta 1 here, and, you know, for my picture, you know, let's assume for the picture that the thetas are distinct. So you have theta 1, theta 2, theta I plus 1, theta n minus 1, and so on, okay? And now a sequence, so we will have now the other sequence, let me put it below it. So mu1 greater or equal to mu2 greater or equal to mu n minus 1. And now let's just write first what the definitions say. So if we take, so in this situation, when m equals n minus 1, n minus m, which is this weird, this term a little bit here that may confuse you, this equals 1. So that inequality over there, this inequality, or inequalities, because they happen for every I, they translate into what? They translate into mu I. I'm going to change the order. I'm going to change the order now just to match what I have here. Less than or equal than theta I and greater or equal than theta I plus 1. Okay? So in this case, perhaps this is the most intuitive case where you can understand what happens for eigenvalue interlacing. You have this bigger sequence, theta 1, theta n with n terms. You have a smaller sequence that has just one less element. You say that this sequence, the smaller sequence, interlaces the bigger sequence if these numbers from the smaller sequence go between the gaps, in the gaps between so basically your mu1 has to be here. You see, inequality here you see is not strict, is with less than or equal, so we'll see in a second that, you know, mu1 can happen to be theta 1, something like that. And then here, this is where mu I goes, and this is where mu n minus 1 goes. Okay? So this is the case where m equals n minus 1. Okay, so I hope this is clear for everyone what happens. It's just you have n numbers, you're going to have n minus 1 gaps between consecutive them. I mean, sometimes the gap will be, if theta 1 and theta 2 are the same, then when you have this interlacing, it's guaranteed that mu1 is going to have to be equal to them as well. Okay? Now, so this is this simplest case when m equals n minus 1. For the general case, what happens, this inequality stays the same. So the bigger matrix beats the small, or the ith is going to be the eigenvalue of a bigger matrix. But for now, the ith entry of the longer sequence beats the ith entry of the smaller sequence. But now what happens when you have n and m differing by more, you're not going to be able to put this mu I just in this interval theta I plus 1. It could be an interval theta I, theta something more here. That interval, it's a bit looser. Okay, so that's all it is. Okay, so in some sense, think about it. If n and m are close, you have kind of close control where the mu's go. Once the difference between n and m becomes larger, your interval in which this mu I can live, it's a little bit loose. Okay. If you have any questions, again, just feel free to ask. But this is a general definition of interlacing, and what we'll do is we'll show various instances in which eigenvalues of matrices, eigenvalues of a smaller matrix will interlace the eigenvalues of a bigger matrix. But this definition, we'll use it throughout today. Okay. So, okay, I'll leave the picture there and I'll erase here and I'll state the main theorem from which everything will be derived. Okay, so as before, this is the theorem that sometimes in the books you'll see it attributed to Courant Hilbert. It works for Hermitian matrices, but we'll do it just for real and symmetric matrices because that's how we'll apply it. So as before, we have two numbers, m and n, like this. N is the bigger one. And now we'll have one matrix. Let A be a matrix with real entries, which is symmetric. And we will denote its eigenvalues accordingly to, we'll have with eigenvalues theta 1 greater or equal to theta 2 greater or equal to theta n. Okay. And for us, we'll need the notation for we'll need a basis of an orthonormal basis of eigenvectors. So I will write it here. So this matrix with eigenvalues and corresponding orthonormal basis of eigenvectors u1, u2, un. Okay. So this is our big matrix, and for us, in the situations when we'll apply it to graphs, this will be adjacency matrix or Laplacian matrix. Most of the application I'll give you today will be adjacency matrix, so just keep that in mind. Okay, now we need a smaller matrix. To do that, let's assume that S is a tall matrix, so it's N and M, such that its columns, the columns of S are orthonormal. So that one you can write it that S transpose S equals identity. Okay, so the picture will be like this. I have, this is A, which is N by N. This is one actor in our story. So this is going to be one actor. And now we're going to have a smaller matrix. And that smaller matrix, we will make it from this S and from A. And that smaller matrix will be like this. You will take, let me see, the other way around. The other way around. So we'll have S transpose okay. So assume that S is like this and denote B S transpose AS. Okay. So now, because S is N and M, S transpose is, you can see from this picture, so this is M, this is N, and M. So this matrix will be a smaller matrix. And now we need to denote its eigenvalues by something. Denote the eigenvalues of B by mu1 greater or equal to mu m. And because A is symmetric, this matrix B will also be symmetric. And so we have an orthonormal basis of eigenvectors, so we'll use one of them. You can have many of them with an orthonormal basis. Orthonormal. Eigenvectors. Let's call it V. V1. V2. V2. Okay. So I'll give you, this theorem has several points, including analyzing something about equality case. So I'll do first just the eigenvalue interlacing part without analyzing the equality case, and then we'll do the one a bit later. So, okay, so you have a big matrix. So from it you make, with this S, you make a smaller matrix. So you have now two symmetric matrices, and now, because I kind of prepared you for it, surprise, surprise, guess what's going to happen, okay? So what will happen is that the eigenvalues of the smaller matrix, so the eigenvalues. So this theorem, like I said, has several parts. I'll just give you the first part now, and then I need some definitions for the remaining part. But the key thing is this first part that I'm showing you here. The eigenvalues of B interlace the eigenvalues of A. Okay. Any questions so far about anything that's... It's a little bit abstract and it kind of falls, you know, in front of you on a rainy morning, so it maybe takes a bit of time to get used to it. But like I said, if you want to keep something guiding you about, you know, what are we doing here, for us, this A will, like I said, today will be adjacency matrix of a graph, and that's how we'll apply it. That's how we're thinking about it. Okay. All right. So let me give you the proof. So what I will prove first, the key thing is to prove the following. So I'll take I from 1 to m, and we will prove that the ith eigenvalue in the big matrix beats the ith eigenvalue in the smaller matrix. And I claim that that's the only thing you actually need to know. Because the other inequality, remember, like, so this eigenvalue interlacing means that for any I, let me write it here, from 1 to m, what do we have? Mu I is less than or equal than theta I and is greater or equal than theta I plus n minus m. So you can, I will give you the proof of this inequality. And then I'll show you that if you know that this is true, you can do a simple trick. Just multiply the matrix by -1 or something like that, and you can get this one for free immediately. Or you can mimic the proof that I will give you now for this part. You can mimic, actually, that's probably a good exercise for you to do, just so that you understand what I'm doing today in this proof. Okay, so I'll just prove this part, and I'm telling you that, you know, once I prove this part, this other part, you have two ways of doing it. The easy way with applying this inequality to the negative of A and seeing how things work, or just repeating the proof that I gave here, but with not quite word by word. You have to change a few things. So here we will prove that mu I is going to be less than or equal than theta I. Okay, so let me say I will make it like this, theta I, just so that hopefully you'll remember what I will do. Essentially, this proof will be by finding some kind of double agent here as before, which will be greater or equal than this, and which will be less than or equal to this. Okay, so that will be the trick of the key idea of the proof. Okay, so that's what we're trying to do. Okay. All right, so now let's denote some things. So first we look at, again, from our the previous max, min, max, all that business, we look at mu I, and we want to show mu I is less than or equal to something. If we remember what we, when you look at this, so let me, when you look at the sequence mu1 greater or equal to mu I greater or equal to mu m, remember that we had to think about mu I from two perspectives, especially like mu1, it's always the max of something, mu m, they're always the mean. So there's no, you know, nothing to talk here. But mu I here, you can look at it from two perspectives. Mu I is the smallest from the beginning, and it's the largest from the end. So if you want to show that mu I is the smallest than something, you kind of have to look from the perspective of what happens on this side. Okay, so that's exactly what we'll do. So so I need just some notation. The first one is pretty easy. I think we've used it before. So denote by VI the span of V1 VI. So it's a span on the first part where lambda I is the smallest Rayleigh quotient. Okay. So this space is going to basically will allow us mu I will need this to you know, we'll need this space to get to lambda I. But now we have to have a connection between the two eigenvalues via some kind of intermediate this double agent that I talked to you about. So now I will define something that at the first glance is going to be a little bit scary. So denote by wi v. So here, if I wanted to write it in, I'll write it like this. This is span of v1 vi. Okay, and maybe let's keep it here so we remember it. Wi, it's the span of v1 vi. And now I will, this is vi, sorry, vi. And now I will need this wi. So the wi will be the following. So this is the orthogonal complement of the span of the following vectors. Let me think how it is. S transpose. Yeah. S transpose U1, S transpose UI minus 1. When you first see like how, you know, who can come up with something like this? Well, they can come, you know, people like that can come up with something like this. You can come up with something like this for the other inequality, okay? So let's write it here. So this will be the span of S transpose U1, S transpose UI minus 1, and we take the orthogonal complement of it. So for now, let's just do small steps, okay? So we'll get to WI when we have to get to WI, which is in 1 minute. But first, VI. What can you say from the definition? What's the dimension of VI? I, okay? So because the V's are orthonormal basis, so we have that dimension of VI is I. Now, I would like to say something about the dimension of WI. Doesn't have to be super precise, but let's start, before we go to the orthogonal complement, let's start with the span of this. Okay? How many vectors do I have here in this set? I minus 1. So before you do anything, you know for sure that the dimension of that span is going to be less than or equal to I minus 1. You don't know for sure it's going to be equal, but let's say less than or equal. You won't need anything else. So if the dimension of what's inside is less than or equal than I minus 1, then the dimension of the orthogonal complement must be, yes, exactly, n minus I plus 1. And now you can kind of get an idea, because we've done these things with dimensions before in another context. You get an idea kind of where this is heading. Okay, dimension of this is I, dimension of this is at least n minus I plus 1. So if you add up the dimensions, you're going to get at least n plus 1. So you will be guaranteed what? Intersection is non-trivial. Okay, so let's just write that down. So therefore, dimension of VI intersect WI equals the dimension of VI plus dimension of WI minus the dimension of their sum. And then this is going to be greater or equal. I mean, here I have I plus n minus I plus 1. This dimension is at most n, so it's going to be greater or equal to minus n, and this will be 1. Yes, question? Yeah.
Dimension of WI because S transpose dy has m component.
Just a second. So S transpose, yeah, so the U's are tall vectors. So S transpose is the long matrix, and the U is also going to be like the U1, for example, would be a, so you see you take rows here, you take this, so this will be This is S transpose U1. So both of these spaces, they are in which dimension? In which of what they're both in Rm. Okay, did I make what am I? Let me see, because I made a mess here. This couldn't be. Okay, so let me. Yeah. I think let me see if I got them mixed up. Just a second. I might have gotten the spaces mixed up. Okay. So just one second. What did I? A is theta. B is mu.
So the span of fundal of A.
Which one? Yeah. But I
So those V's are identifiers of B.
the V's. Yes, the V's are of B. But what did I mess up here? Yeah. So I think I just messed up the dimension here. Yeah, this is probably M. Yeah, sorry. That's all. Thank you. Okay. So these are the V's. They come from the matrix B, which is in M. So this is in Rm, and here the U's are tall, but this is also in Rm. Okay. Yeah. Thank you. Very good. Okay. So again, here what we get is this dimension is at least one. Hence, there is some vector. You see how I call it? Si, which belongs to Vi intersect Wi, and Si is not going to be 0. Okay. So this Si is going to play the role of double agent here. So this Si we'll try to play it because it's in two subspaces. We're going to try to get information from each of those subspaces, some inequality. Okay. Okay. Let me erase here. Okay, first the easy part. So we have Si belongs to Vi. Vi was the span of the vectors V1, V2, Vi. So obviously also Si is not 0. What does it imply about, so these were the vectors corresponding to mu1 greater or equal to mu I. So what's going to be the relation between mu I and Si transpose B Si, the Rayleigh quotient here? Less than or equal. So okay, so that part again, this is the thing that we did for, I think I showed you for largest eigenvalue, but you can do the same thing because SI is in here. You write it as a linear combination of these vectors. You plug it into here. You'll get a convex combination of the eigenvalues from mu I to from mu1 to mu I. Mu I is the smallest, so that convex combination will be greater or equal than mu I. Okay. Now here, let's just see a little bit if we can. Again, it's a double agent, so this is one side of the story. Now let's see, obviously you would like to continue this and get on the other side that this is less than or equal than theta I. Now B had a formula, this formula, so you have SI transpose, S transpose, AS SI divided by SI transpose SI. So now, you see this place here is where everything switches from B is going to switch to A. It's a different vector. Here, this is a Rayleigh quotient for B with SI. This will be a Rayleigh quotient. It doesn't look like it now, but it will be a Rayleigh quotient for the matrix A with a different vector. Now, from the top, you kind of see what the vector is going to be. So you can write this as SI transpose A SSI. Now, at the bottom, you have something like this, which maybe doesn't look like the inner product of these two, but maybe it does, because what did you know about S? S transpose S is identity. This is the place, okay? So this thing, so let me write it here, SI transpose SI will equal, you can do SI transpose S transpose S SI, because this one is identity. And then it's the same thing as SI transpose SI. So that's what I'll write it here. Okay. Now we're not done. We're almost there. We have mu I. We related to this Rayleigh quotient of this vector SI. We switch from B to A. We got to a Rayleigh quotient of something. But now I have to, in order to say something about this Rayleigh quotient, I need to understand where this SSI, where does it live? And now we have to, here, you see here, we've used the part that SI belongs to VI, but SI also belongs to WI, and we haven't used that yet. So WI is the weird thing there. Okay, so let's use that. So I'll do it here. Because SI belongs to WI, what do we get? So WI is an orthogonal complement of something. So if you're an orthogonal complement of something, you must be perpendicular to everything in that something. So you must be perpendicular on all the vectors in the span, which you have them there. So it means that SI transpose, let's say S transpose S1 equals all the way to SI transpose S transpose S1 equals 0. Because you have to look, see, like the WI is the span of these I minus 1 vectors. So then, because the SI is in here, it has to be perpendicular on all of them. And again, it's real and symmetric, so I can just write the inner product like that. So we have this, which means now, here I have this vector. So I will transform this part in terms of that vector, which is the same as SSI transpose S1 SSI transpose, here this should be SI minus 1, sorry. Yes, thank you. U, thank you, U. U1, UI minus 1. Thank you. So what does this mean? This is the same as S as this vector belonging to what? You can say two ways. It belongs to the orthogonal complement of U1 ui minus 1, like this. But because you have a whole basis there that I erased it, U1 all the way to UN, you know exactly, you can rephrase this as the span of UI all the way to UN. So by this this kind of little bit piece of magic, at the same time you have something, you have one vector which is SI, which belongs to the span of these things from the beginning, and then you do something to that SI, and you have a vector which belongs to here. And okay, so now the U's are eigenvectors for A, and by the same argument as before, this implies what can you say now about this the Rayleigh quotient SSI transpose A SSI transpose divided by transpose here and theta I. Which one wins on this side? Less than right. So this Rayleigh quotient is a very important thing because it allows you to relate these eigenvalues to each other. And in this situation, again, this is a little bit of a to me, it still feels an amazing, it's an amazing result because you can, like I said, you can have this double agent SI. So you have here SI transpose B SI. And then you switch from B to A, and somehow things are, you have a different perspective. So maybe erase there. This is the what is it? A bit of a magic. So one side, this side. So okay. So that's the proof. Yeah, I hope I didn't make any other typos through in the proof. Does anybody have any questions? Again, see, I've gone through this. I've taught this type of theorem several times to my students, and it's still like the details are a bit technical. So don't feel intimidated by it at the beginning. I mean, the only way you remember this, you have to write and rewrite the proofs a few times. So that's why I would suggest you do the exercise number. I thought we already had 19. 90? No. That's a new record. Okay, exercise 19. Prove that theta I plus n minus m less than or equal than mu I. 20. He's trying to get out of doing exercises, so he's giving smaller numbers. So, okay. So try to, like I said, I mean, both proofs will be straightforward. One is just mimic this proof, and I think that's useful for you to do so that it will help you understand this proof better. Because here you just have to pick up the right subspaces. And again, if you're troubled by how to do it, think about again from this perspective of mu I. Mu I greater or equal to something that will allow you to choose the subspace there from I going down, and then you need to again to choose a subspace to choose what you do here. Think about dimensions and think about a little bit how we did there. Again, like I said, that's the proof kind of mimicking this proof. And then there's an easier proof, like I said, the shorter proof, where you just apply the theorem that we just proved. You apply it to, if I have A and B, you replace you apply it to minus A and minus B. And when you change the order, the indices will change in the way you want it. So it will work out. Okay. All right. So let me see. Okay. So this is the first part of the theorem. In order to tell you about so I will erase and just write it on the board, and then I'll tell you about something related to equality case. So let's just maybe keep it here. So again, A what did we have? We had U1 here, U2, UN, then S. So A is a big matrix. S is S transpose S is IM, and then you have we have from it we have B, which is this matrix, and B will have eigenvalues mu1, mu I, mu m, and v1, vi, vm. And the main result here is again that mu I is going to be less than or equal than theta I, greater or equal than theta I plus n minus n for any I. Okay? Now I'll give you a definition. So here it may happen that you have equalities in this inequalities because they're not strict. And if you have equalities in pretty much all of them, you have something called interlacing is tight. So we say, so I'll just apply it for a general definition of mu and theta, mu interlacing theta. So we say that the interlacing is tight if there is some number, let's call it L, such that mu I equals theta I for I from 1 to L, and mu I equals theta I plus n minus 1 for I from L plus 1 to M. So if you had the theta 1, theta 2, theta I plus 1, theta n, and so on. So mu I will hit here, mu1, mu2 will be as, so the first mu's will be as large as possible. So this will be your mu i's. And after that, as you go down, so this one you kind of look from the back end towards. So here, if I have I equals m, mu m equals theta n. So this is here, this is where I will have mu m. When I have here theta n minus 1, this is where I will have mu m minus 1. And then you figure out what should be for mu L plus 1. So what theta should be here? Theta of, just plug it in. Okay. So on the first on the top, the mu's are as large as possible. On the other side, at some point, it switches, and on the other side, all of the mu's are as you know, like as small as possible. Because you see, like our inequality is this one. It's always guaranteed. So when you start from the top, from 1, 2, up to L, the mu I is achieved its potential. It's as high as it can be. But when you look from the end, when you look from the m all the way to L plus 1, this mu I will be here. Okay. So now this is not super important now. It will come up into play a little bit later, but for now, just yeah, just write it down and okay. So, like I said, the Courant-Hilbert theorem has other parts. So you have second part, and I erased on the board, we had this thing with the double agent. You know, the double agent plays the theta I versus the mu I. Well, you can ask yourself, what happens if you have equality? If you want to analyze something about interlacing tight, first you can want to understand what happens if mu I actually equals theta I. And you have that, I wrote it in the corner there, you have theta I, you have this Rayleigh quotient in between them, and then you have mu I. So it's if the walls are tight, so the theta I equals mu I means everybody has to be equal there. So that's what I say. If mu I equals theta I for some I, then B has some eigenvector. That eigenvector will be that SI there. So, but for now, we'll just call it differently. Let's call it V, such that SV is an eigenvector of A. So if you go look through that proof, if you have equality in, look through your notes, if you have equality in theta I equals mu I, then those Rayleigh quotients have to equal both eigenvalues. And you have the Rayleigh quotient, you had that vector SI coming from the space V1 all the way to Vi. So in order to the Rayleigh quotient of it to equal mu I, it has to be an eigenvector. And then on the other side, it also has to happen that S times that vector has to be an eigenvector for A. So that's exactly what this is saying. So do we make it exercise so that low-hanging fruit? Okay, now you remember the number. Exercise 21. Very good. Okay. And then, so there's another part 3. Okay, let's write the, okay. I'll just put 3 the following. If the interlacing is tight, so if you have interlacing is tight, then what you will have something of this form: AS equals SP. So this is, you have to be careful when you're dealing with this matrices. We know that this is the case, and you know that S transpose S is IM, but I cannot just make this S transpose from here, move to the left, and get this in general. But if the interlacing is tight, it's actually, I'm not doing that, but you can actually show that this is the case. And you can use to do that, okay? So if you have interlacing is tight, you have a closer connection, you have a stronger connection between A and B than this, okay? So clearly this implies this, but this doesn't imply this, okay? Yes? Yeah, yes, very good. So this eigenvector corresponding, very good, to mu I, such that SV is an eigenvector of A corresponding to the same eigenvalue, but to theta I. But theta I and mu I are the same. Okay, so this is a close connection. We've kind of seen this type of thing. This is a bit different, more general, but we've seen something in this equitable partition business. But okay, so okay, all right. So this is a general theorem, and now let me show you two applications for graph theory. Okay, that's what we want to do. Yes.
Like, what actually this S matrix is doing to the A matrix in terms of the column space of A matrix?
Which one?
Like B equal to S transpose S. How?
Well,
I'm asking in terms of the column space of A and
well, I mean, what does this do when you multiply A by a matrix to the right?
not even in the type case, but also the other case also.
So let's see it for the graph theory case. So then you will see like maybe like something concrete, because here it's for the matrices. It may be a little bit, it may be a little bit. But let's see for the graphs, and you can see what happens there. Okay, so the first application, so consequences or applications. This is called Cauchy interlacing. And it says the following, let A be, again, it applies to Hermitian matrices, but for us, we'll just need the real and symmetric. Symmetric matrix, be a symmetric matrix. Now, Professor Kanan recalled to you the notion of principal submatrix and so on. So so principal submatrix, you just delete some rows and you delete the same column, the corresponding columns. So what happens is the eigenvalues of any principal submatrix of A interlace the eigenvalues of A. Equivalently, if you have any real and symmetric matrix, you delete some rows, you delete the same columns. Obviously, the matrix you get is also real and symmetric. It has real eigenvalues. So the eigenvalues, so in this case, your A is this, and maybe the simplest case you can think about the B is you delete the first row and the first column. Okay? Of course, if you, depending on the situation, you may want to delete more. But this is, okay, again, this is a general theorem for, like I said, it's true for Hermitian matrices. Here we go to real and symmetric, and then we'll do one more step. We'll go for graphs to tell you what it means for graphs. Okay? So, So eigenvalue interlacing for graphs. So Cauchy, so this is, I'll do it just for the adjacency matrix. Let gamma be a graph. If gamma prime is an induced, so this is the keyword, induced subgraph of gamma, then the eigenvalues of the adjacency matrix of gamma prime interlace the eigenvalues of the adjacency matrix of gamma. Okay, so it's clear how this implies this, because an induced subgraph, the easiest way to remember what's an induced subgraph is, so it's a subgraph which is obtained from the original graph by deleting some vertices, possibly none. So you just delete vertices, you leave all the edges intact. I mean, obviously, if you delete a vertex, you delete those edges, but the other ones, you leave them the same. So it's important to know the distinction, and here, this is very important, that when you apply Cauchy interlacing for graph, it has to be an induced. Or if you take this, so you have to be careful. Professor Canano will talk about Laplacian matrix later. So if you try to apply something to Laplacian matrix, you have to be careful, because if I have a Laplacian matrix, I have those things on the diagonal, which are the degrees. So if I take a principal submatrix of the Laplacian, I can apply Cauchy interlacing. It's okay. But if I take an induced subgraph of the graph, the Laplacian of it is not going to, very likely is not going to be the principal submatrix of the Laplacian of the big graph, because those degrees will be messed up. Okay. Now, so it should be clear how this implies this. Now, how does this imply this? Because here, this is general, this is the S something. So maybe I'll change the picture. Let me see how. So let's say I like the first row and first column now. I want to delete the last row and the last column, or something like that. So you can have B, and maybe you want to delete more, something like that. So here you have your A. You don't have a B, but to get a B, you need an S. So let's say my principal submatrix, it's something like this, like on the first, what did I use? Let's say this is on the first M and M. Okay, for simplicity, I can assume that. So I do that by using the matrix S, which is N by M. And here you put identity matrix on the first M rows, and then you put the zero matrix N minus M. So this is kind of if you want a matrix whose columns are orthonormal, this is maybe the first thing that you're going to think about. You know, like the canonical vectors. You know, these are the basis vectors if you look down. And then if you apply S transpose AS, this kills off all these rows. So yeah, do it, and then you get this principal submatrix. Okay. So Cauchy interlacing. I mean, there are different proofs of Cauchy interlacing. If you look in the book by Gottsil and Royal, They give more like an analytical something with power series and functions, poles of functions, and so on. You can read that proof. It's a little bit different than what is here. But here, Cauchy interlacing just falls from this big theorem. Good. Okay. So that is one. Okay, for graphs. And then for the second one is called Hammer's interlacing. And for this Hammer's interlacing, so this is one. I mean, Hammers didn't call it that, but he obtained this in his, so this is Wilhelm Hammers in his PhD thesis, 1978. But if you want a very good like overview of it, it's not so recent, but it contains more examples than I'll give you here this week. You can look of, he has a paper in LAA, interlacing, I think it's called interlacing and graphs. I think you can find it online, and it has a lot of examples of applying the Hammer's interlacing, which I haven't told you what it is. Okay, so let me tell you what it is. Now, here, do not confuse what I'll tell you with the equitable partition stuff that we talked about yesterday, because there are some things that will be similar, like a partition, we'll talk about partitions and so on. But the partitions that I'll talk about here, they don't have to be equitable. They may happen to be, but they're general partitions, okay? So, okay, so let me define something also called quotient matrix, but here's how we're going to define. So assume, again, we have a graph. Assume that V, we have, again, phi. Let me change the, I don't want K, I will put M. Let's say this V1, Vm is a partition of V. So V1, V2, Vm. Let me do it, so yeah, obviously that's my general graph. Let me do it on a particular graph here. Let's take our favorite graph, this one. And let me take this partition to be something simple. This triangle, this is V1. Yeah, that's, no, I don't want that because it will be equitable. Let me take this part to be V1 and these two vertices on this side to be V2. Okay? So now, for any partition, you can define, so you can define, we define the quotient, the quotient matrix. Let me call it B, which is B of pi, associated with pi, as follows. So this will be Bij as before, I and j from 1 to m, associated. So what do we have? We have a Vi here, we have a Vj here. Now, in equitable partition, everybody in Vi had the same number of neighbors here. Here, it may not happen. You can have some vertex has 2, some vertex has 1, some vertex has none. Okay? So I will define Bij as the average of the number of neighbors of a vertex from here that live in here. The other way to look at it is you count the number of edges. Count the number of edges between Vi and Vj. Let's call it EVI Vj. And you divide by the cardinality of Vi. Okay? So this Bij is EVI Vj divided by cardinality of Vi. Because again, in between these two parts, what's the number of edges? It's the sum of the neighbors of the vertices in here, neighbors that live in here. And then you average by the number of vertices that live in here, which is cardinality of Vi. Okay, so let's just do this example here. I'm sorry for messing up. Let me draw a different picture so that you can see. Let's see. So this is V1 and this is V2. So what will be the matrix here? The same thing as before. If Vi and Vj, so the same thing as before. If Vi and Vj are the same, then Vi, it counts the number of edges twice. So on the diagonal entries, you get the average degree inside Vi. So here, V1, you have here, this vertex has degree 2, this vertex has degree, the average degree inside here. So this vertex has degree 1 here, degree 1 here, degree 2 here. So this is going to be 4/3. And then you count, you're going to divide by 3 because you have 3 vertices in here. And like I said, the simplest way, you could take each vertex individually and add up the degrees, but you can just count the number of edges in between. So you have 1, 2, 3, 4. So it just happened to be 4/3. Backwards from here, in V2 we have 2 vertices, and we already calculated that we have 4 edges, so it's 4 over there. And inside here we have 0.
Should the counting edge first component will be
Which one?
first entry.
4, 3?
So it can be first entry will not come 4 by 3. 2 by 3.
Here?
Counting edge is divided by.
Yeah, so you look inside here, and inside V1 you just have these 2 edges. So the sum of the degree will be 2 times 2, which is 4. And you divide by the number of vertices. So here I said if Vi and Vj are the same, then this will, what I'll do here, it will be twice the number of edges. We'll count each edge twice. Okay? So essentially you count for general I and j, you will always count the average number of neighbors. It's of the vertices, so you take all the vertices in Vi. For each of them you count how many neighbors they have in Vj, and you average. Now if Vi and Vj are the same, it means that I look at every vertex in Vi. So here I have 1, 2, 3 vertices in V1. How many, what's the degree of each vertex inside V1? Well, this vertex here in the big graph has degree 2, but inside V1 has degree 1. This vertex has degree 2 here. It has 4 in general, but 2 in. And this one also has degree 1. So if I sum up, 1 plus 2 plus 1 is 4 divided by 3. Make sense? Yeah. Okay. So this matrix is not going to be, obviously you see, is not going to be as nice as integers for quotient matrices and so on. You get like some weird numbers. Okay. Now, let me state you the result. So I'll erase here. And you saw the example, like this matrix is not even, it's not even symmetric. Now what will happen is, 1, the eigenvalues, so this will be kind of understood, but B, even though it's not symmetric, will show that it's similar to a symmetric matrix. So B will have real eigenvalues. So the eigenvalues of B interlace the eigenvalues of A. So the game here, the way you should think about it is, you have some kind of structure in your graph. You have some kind of combinatorial parameter that you're looking for. So that imposes some kind of constraint on the structure of your graph. So based on that, you partition your graph into some parts. We'll show some example in a second, like 2 parts, something simple, but sometimes it could be more parts. Now, what will happen is this B will contain in it some information about that combinatorial parameter that you're looking for. It will contain something about combinatorial properties that you're searching for. And then ideally B is small enough, easy enough that you can calculate its eigenvalues relatively easily, okay? And then what you can do is, by this interlacing, you relate this B, which will carry some kind of, B is a matrix, so its eigenvalues are spectral things, but they will carry some kind of information about the structure of the graph, and you'll relate it to the eigenvalues of the big graph. So that's kind of the gist of it. And I forgot to say that that's the same thing with Cauchy interlacing, okay? Okay, so that's, okay. Now, here's the second part. If the eigenvalue interlacing is tight, which is this definition that I gave you here, then you can say that the partition that you have is equitable. Then the partition yes. Well, you know for sure that if the partition is equitable, you know that your eigenvalues from that quotient matrix will be eigenvalues of the big thing. I don't know off the top of my head if you can tell that they line up the way you want it. You know, like as for to have interlacing tight, you need these eigenvalues to line up, you know, the way you want it. Yeah. So, but yeah. Okay. So let me give you one examples for each situation. We'll do some more later in the class, but then we can stop. So I have Hammer's interlacing, Cauchy interlacing. Let me erase it. Okay. So again, another application examples. So this one is called, so this is for independence number. Do I need to give the definition? Does everybody know what an independence number is? No? Okay. No or yes? No? Okay. So again, let gamma be a graph. An independent set. Well, let's this. We say that S, a subset of V, is an independent set of gamma. So it's an independent set if there are no edges with both endpoints in S. Okay, if gamma has no edges with both endpoints in S. So this is our graph. Independent set, this one. So this is an independent set. You see, because these 3 fat vertices, there are no edges between them, okay? Now, the independence number of a graph alpha gamma of gamma is defined as the maximum size of an independent set of gamma. So alpha of gamma is the max of the cardinality of S as independent set. Okay, so just because I gave you an independent set here, you check that it's independent set. So this picture, it doesn't tell me that alpha of this graph is 3, because this is a maximum. So when you give me an independent set and you verify that it's independent set, you just give me a lower bound. You just say, this picture tells me that alpha of gamma is greater or equal to 3. How can you, is this the right? Is alpha equal to 3? You can see if you can find something with 4, okay? But even if you find something with 4, the question is the independent set with 4 vertices, is that the largest size that you can find? So again, for this independence number, so alpha of gamma, if you want to find lower bounds, those are, you can just try to do by example. Or sometimes there are things like probabilistic method in which people try to prove things via existing, show that something exists. So you have to, if you want to prove that alpha is greater or equal to t, you have to convince me that there is an independent set in your graph which has t vertices. You either just give it to me like on the picture, hey, 3, or give me a proof or something for a modular. Now, what do you do here? So when you're trying to find this independent set, you'll try to find it exactly. And in general, this is a difficult problem computationally, like there's all this complexity theory about it, but you like to find something, okay, how do I find an upper bound for the independence number? Well, you can say, well, I'm going to take an independent set S, and somehow I will require a proof. I will prove that the cardinality of it is at most this much. So here, it doesn't work by example. Here you have to prove something, okay? So that's what I will give you now some places where you can get an upper bound by proving something. Okay. Okay, so let me give you an upper bound for the independence. So this is called Kvetkovich inertia bound, because it has something to do with the number of positive, negative eigenvalues. So what it says is that if gamma is a graph with n vertices, then the independence number of gamma is going to be less than or equal. I'll write this in 2 ways. It's the minimum of n minus n plus and n minus n minus, where n plus is the number of positive eigenvalues of A, and n minus is the number of negative eigenvalues. And so the A is the adjacency matrix. So A has positive, negative, and also 0 eigenvalues. Okay? So So A is the adjacency matrix of gamma, and when you look at its eigenvalues, let's say 0 is here, so everything from here to here, if you count, you will get n plus. If you have something here, obviously at 0, you will count n0 because 0 may have a multiplicity, okay? And then from here to here, you will have n minus. So this is maybe theta 1. You go here to some kind of theta, I don't know. This is theta n. Okay? And so n, my n, it's the n minus, n0, and n plus. So you can rephrase this if you don't like it, n minus, n plus, plus n minus. You can write it n0 plus the minimum of, because n minus, n plus, this is the same thing as n0 plus n minus. N minus, n minus is n0 plus n plus. So you can write it like this. But either way, so alpha of gamma gives you an upper bound. Maybe this is the easiest because let's say n minus n minus. How can you say it in words? It is the number of eigenvalues of which are non-negative, yes. So this is the number of eigenvalues. So I'll change it here for lambda because we have lambda when we have this. Eigenvalues of A that are non-negative. Okay, so let me, how did he prove this? So the proof is, it's very simple. What you have is so assume that M is the independent number. You have to denote it by something. And consider an independent set with cardinality of S is M. So you have M vertices such that no two of them are adjacent to each other. Now, what do you think about, what can you say about the principal submatrix of the graph, which corresponds to the vertices in S? It's a zero matrix. So without loss of generality, I can assume that A looks like this. That this S, the vertices in S are at the beginning, and I have here just a giant 0. Okay? Okay, so the B matrix for me will be this. This is my principal submatrix, which, you know, this is the easiest case because you can calculate. You know the eigenvalues. Okay? So what does Cauchy interlacing tell you? Something. So you have to write down what Cauchy interlacing tells you. So from Cauchy, you can get that lambda, the mth largest eigenvalue of my graph, is greater or equal than the mth largest eigenvalue of B. What is the mth largest eigenvalue of B? 0. Okay? So then let's do a picture. Let me erase it. So you have 0 here, lambda n is somewhere here. So we're trying to place this. So lambda m a is somewhere here. It's kind of, you know, it could be here, but it could be in the, you know, 0, okay? Now, the other thing that you will get is you look on the other side. So remember, our interlacing was something like mu I less than or equal than theta I. And this is what we used already. But you also have something of the form mu I equals theta I plus n minus m. And here, it makes sense to go to the first one. So let me write this so this will be lambda I of b less than or equal than lambda I of a greater or equal than lambda I plus n minus m of a. We use this. What do you use it? At m. So we use this I equals m. And we will use this one at I equals 1. So if you take I equals 1, you know this is 0. So 0 is going to be greater or equal than lambda 1 plus n minus ma. So lambda m is there, and lambda n minus m plus 1a is here, somewhere here. Now, so lambda m is here, so it means that a has at least how many non-negative eigenvalues? At least m, because lambda m is greater or equal to 0. It's at least m non-negative. But what was the precise number of non-negative eigenvalues? N minus n minus n minus. So because the total number of, let me erase here. So this tells me that n minus n minus is greater or equal to m. It kind of just falls into your lap because of this. Okay. Now, what do you think happens on the other side? Lambda n minus m plus 1. So if you count from back, this is n, this is you count, this would be the first from the back. This is going to be the mth from the back. So it's the same argument. So A has at least m non-positive eigenvalue. And you get n minus n m plus is greater or equal to m. And that's exactly this. Okay. So it's a bit weird to think about it this way, but in this situation, you see what are you looking for? Independent set. What's an independent set in terms of linear algebra? It's the same thing as a principal submatrix, which is all 0. Okay, what do I know about principal matrices? Cauchy interlacing. What does that mean in terms of, it means this. It means an upper bound. So I'll stop here, and we will do in the afternoon, we'll do application of Hammerly interlacing, and I'll show you examples where we can apply this inequality for like some simple graphs like Peterson graph and so on, and we'll see how it works. Okay, so do I have more time, or is I finish? Finish? Yeah, okay, I'll stop here. Thank you.
Okay. Good morning. Okay. Yeah. So today we'll discuss about Laplacian matrices. So before defining the Laplacian matrix, we'll discuss about incidence matrix. Okay. It's also called a signed incidence matrix. You can think of. So given a graph G with the vertex at V and edge at E, let us give a labeling to them. Let V12, Vn be the vertices and E12, Em be the edges. Okay. So given a graph, I can associate something called incidence matrix. Is denoted by Q. So this is an n by m matrix. Okay, this is an n by m matrix. The rows are indexed by the vertices. Okay, v1, v2 to vn, and the columns are indexed by the edges. Okay, this is your matrix. The definition is Qij is so you look at the edge. Okay, so before that, before defining it, given so we are working with a simple graph, simple undirected graph. First, to give a orientation to all the edges. Okay, fix the orientation to all the edges. So after giving the orientation, if you take an edge, every edge will have a starting point and the ending point. Okay, a starting vertex or an end vertex. For an example, so if you take this graph, this is V1, V2, V3, V4. Let me give name to the edges E1, E2, E3, E4, E5. So this is a graph given to us. So for defining the incidence matrix, first we have to fix an orientation. By orientation, I mean give direction to all the edges. Okay. After giving the direction, just fix it. Okay. We will define the incidence matrix for this orientation. If we change the orientation, the incidence matrix will change. Okay. The idea is this. You look at the column corresponding to the edge E1. Okay. So you put a -1 where the edge starts. Okay. So it starts at V1. So keep a 1 in the V1th place. Where it ends, keep a -1 there. Okay. -1 here. The rest of the places keep 0. Okay. Similarly for all other edges, we do this thing. E2, E3, E4, E5. So E1, E2 starts at V2. So keep a 1 here. It ends at V3. So -1, 0, 0. What about E3? 0, 0, -1, 1. For E4, 0, 1, 0, -1. For E5, 1, 0, 0, -1. Okay. So we will define the Laplacian using this incidence matrix. So one reason is this definition of Laplacian using incidence. This extends for higher dimensional hypergraphs and other structures also. Okay. So how to write this? So ijth entry of the matrix Q is equal to 1 if the edge Ej starts at the vertex Vi. This is -1 if the edge Ej ends or terminates at Vi, 0 otherwise. Okay. So some simple observations we can do. What about the column sums of this matrix? The column sums are always equal to 0. So because columns are always equal to 0. That means that if you take the vector E of appropriate size, E means all ones vector, that will be in the left null space of this matrix Q. Okay, E into Q is equal to 0 you will get. And one more thing, how many non-zero entries will be there in the rows? Degree of that vertex. If I fix the ith row, in the number of non-zero entries in the ith row gives you the degree of the vertex Vi. Okay. Now, if G is a connected graph, okay, so we already observed that this all ones vector is in the left null space of this matrix Q. Okay, so this is an n by m matrix. So rank cannot be more than n minus 1, because already we observed that the all ones vector in the left null space, the rank cannot be, rank should be less than or equal to n minus 1. So if we are working with a connected graph, then the rank of the incidence matrix is exactly equal to n minus 1. Okay, so we'll prove that first. If G is a connected graph on n vertices, then rank of the incidence matrix is equal to n minus 1. Okay. So what's the proof? So we will use the left null space argument. So if I take any arbitrary vector, okay, so first we will start with the all ones observation. Let E denotes the all ones vector. Okay, which is in, call this is in Rn. Then E into Q, or E transpose into Q, this is equal to 0. Okay, so this tells us that rank of Q of G is at most n minus 1. Okay, now we will take some arbitrary vector in the left null space of Q, and we will show that that should be multiple of this all ones vector. If I can show that, then I am done.
So E is a column vector.
E is the column. So this is n 1 by n transpose I will take. Okay, yeah, thanks. So now let us take some arbitrary vector x in Rn such that x transpose Q is equal to 0. Okay, so the entries of x are given by x1, x2 up to xn. Okay, so if you take the vector x and if you multiply that with the first column of Q, what you will get? If you take this vector, if you multiply with the first column of Q, what are you going to get? What are the entries of the first column? The entries of the first column are 1, minus 1 or 0. Okay, so you are going to get exactly two non-zero entries in the first column. One is 1, the other one is minus 1. 1 corresponds to the vertex where the edge E1 starts, and minus 1 corresponds to the vertex where the edge E1 ends. Okay, so what I will get? So if E1 is the edge Ij, then xi minus xj, this is equal to 0. Okay, in general, if two vertices, okay, I used, let's say I1 and I2 are adjacent, then the component of the vector which I have taken from the null space of left null space of Q, they should have same entry. Okay, whenever you have an edge between the vertices I1 and I2, look at the column corresponding to that edge connecting them. Okay, that column contains 1, 1, 1 minus 1, rest of them are 0. So the non-zero entries corresponds to the xi and xj. So xi minus xj equal to 0. Hence you are getting xi1 equal to xi2. Now we didn't use the fact that the graph is connected so far. Now if you use the fact graph G is connected, then what do you get? If I take two arbitrary vertices, between any two vertices of the connected graph, you have a path. So along that path, we are going to get all the terms of the vector x are constant, same. Okay, that shows that x should be a multiple of this all ones vector. Okay, since G is connected between any two vertices of G, we have a path connecting them, and along that path, or the value of xi on the vertices in the path the values of all xi's on the vertices in that path are the same, are equal. Okay, that is x is just some constant multiple of e. Okay, so this shows that if G is a connected graph, then rank of the incidence matrix is n minus 1. Okay. So in fact, something more can be said. If it is a graph on n vertices, if it has k components, okay, so maybe you can use the same argument to show that if G is a graph on n vertices with the k components, then rank of Q of G is n minus k. Okay, how to prove this? To use the block matrix argument. If G1 to Gk are the components of G, then what is Q of G? You can order the vertices of the graph and the edges of the graph in such a way that you keep all the vertices and the edges in the first block of the rows and first block of the columns. Okay, so it will be a diagonal matrix. So this is Q of G1, 0, 0, 0, Q of G2, 0. Now for each of the components, you can apply the result which we put here. So that is going to give you, this implies rank of Q of G is equal to n minus k. In fact, the converse is also true. If rank of Q of G is equal to n minus 1, then G should be connected. How to see that? Just think proof by contradiction, you will get the answer. How to see that? If rank of Q of G is equal to n minus 1, then the graph should be connected. Okay, I'm saying think of proof by contradiction. Suppose G is not connected, then you can decompose the graph into, let's say, G1, G2, such that between G1 and G2 there is no edge. Now then Q of G can be partitioned into Q of G1, 0, 0, Q of G2. Okay. Now can you give me two linearly independent eigenvectors left eigenvectors for this one. Okay, corresponding to G1 block, keep all ones and rest of them 0. Okay, and then the second eigenvector is first keep zeros in the components corresponding to G1. In the components corresponding to G2, keep all ones. That's going to give you two linearly independent eigenvectors. That contradicts the rank.
Also follows from this one. If the rank is n minus 1 and you know rank is n minus k, then k has to be 1. It's the same.
Can you repeat?
So if the rank, because you're trying to prove the converse, if the rank is n minus 1,
Yes.
You already know that the rank is n minus the number of components.
Yes, yes, yeah, that's also.
Yeah.
Yes. Okay, good. Is it okay? So now maybe with this we will define the notion of Laplacian. So Laplacian is okay. So the same setup. G is a simple graph. So the Laplacian is again an n by n matrix. It is defined in this way. The ijth entry of the matrix is keep the degree of that vertex in the diagonal. If I equal to j, keep a -1. If I is not equal to j and I is adjacent to j, 0 otherwise. Okay, so we have seen about adjacency matrices. This Laplacian also can be equivalently defined in this way. The same, I'm just rewriting. This is d of g minus a of g. But d of g is the diagonal matrix whose diagonal entries are degrees of the corresponding vertices, and the a of g is the adjacency matrix. Adjacency matrix. Okay. So the first result I'm going to prove is kind of easy to see. For any graph G, the Laplacian of G is given by Q of G into QG transpose. Right? It's an n by n matrix here. So again, I will show only for one row or one column. The rest of the things you can prove by your own. Okay. So statement clear? Okay. So so let us look at some entry. First, we'll start with some diagonal entry. I-ith entry. How do you get the I-ith entry? The I-ith entry of the Laplacian take the ith row of Q of G and take the ith column. Okay. So how many? What are the non-zero entries in the ith row? Everything is either +1 or -1. So how many non-zero entries are there? You will get degree of that vertex. Okay, and you are going to take the dot product with the transpose of the same vector. Okay, hence you are going to get the degree of that vertex. Okay, what about the off diagonal entry? For I not equal to j, the ijth entry is so I is different from j. Okay, so if I had to get a non-zero entry, non-zero term, I'm taking the product of two vectors. Okay, so if the places of ones and minus ones in the both the non-zero vectors, if they are disjoint, then I'm going to get 0. Okay, I will get non-zero entry only when there is a overlapping in the non-zero places. When you get a overlapping in this orientation, so we are fixing whenever I'm talking about Q of G, I'm having a orientation there. Okay, so in that orientation, that edge EI, not the edge EJ incident or starts at the vertex I or ends at the vertex I. Okay. So if it starts at the vertex I, then I'm going to get 1 in the common non-zero place. If it ends at that vertex, then I'm going to get minus 1 in the so sorry, wait, what I'm saying. Yeah. So let us write down that. Okay. So in the ith row, I'm going to get the row corresponding to the vertex. That vertex consists of some 1, 0, minus 1 and so on. The column corresponding to ej is I'm going to get 1, 1 and 1 minus 1. Okay. Rest of the entries are 0. Yes.
Actually, in the columns of Q transpose itself is of again the same some other row.
Some other row only. So okay, you are right. Some other row, it consists of 0, 1, minus 1, zeros and so on. Okay. So we claim that this will be minus 1 if the indices I is adjacent to j. Okay, that is the edge starts at I, ends at j, or the edge starts at j and ends at I. Okay, these are the only two possibilities. So either here you will get a 1 here, corresponding to that 1, you will get a minus 1 here, or you get a minus 1 here, corresponding to that you will get a plus 1 there. Okay, if there is no edge between them, then it will be 0. Okay, what is the advantage of having this type of representation, this formula? Positive semi-definite. The moment you are writing a matrix as a product of two matrices of this form, B transpose something like this, then you get it's a positive semi-definite matrix. Okay, so that is one observation. This Laplacian is a positive semi-definite matrix. So this is a symmetric matrix, symmetric and positive semi-definite. So all the eigenvalues I can arrange in this way. So lambda 1 less than or equal to lambda 2 or equal to lambda n. These are the eigenvalues of the Laplacian. Okay. Something more can be said about this L of G. What are the row sums of this matrix L of G? The row sum of the matrix L of G is 0, because if you take all ones vector again, L of G into E, this will be 0 into all ones vector. So 0 is always an eigenvalue corresponding to the eigenvector all ones vector. Okay, so 0 is always an eigenvalue irrespective of the graph. Okay, now the second smallest eigenvalue, this lambda 2, will tell you whether your graph is connected or not. Okay, so that we have already seen that. What is rank of L of G? Rank of L of G is rank of Q of G transpose into Q of G. So one of the fundamental theorem in linear algebra, rank of A transpose A is same as rank of A. So if lambda 2 equal to 0, then rank of L of G is at most n minus 2. That means that rank of Q of G is at most n minus 2. That means that this graph G should be a disconnected graph. Okay, so if lambda 2 is equal to 0, then the graph G is disconnected. If in fact, if and only if G is disconnected, and if the graph is disconnected, if G is disconnected, again a similar type of argument will tell you, then lambda 2 is equal to 0. Okay, so lambda 2 is an eigenvalue. This is an algebraic property or algebraic number associated with the matrix. Okay, so this tells you whether your graph is connected or not. Okay, so for this reason, Fiedler called this second smallest eigenvalue of the Laplacian as algebraic connectivity. So it measures, or it tells whether your graph is connected or not. So by looking at the second smallest eigenvalue of the Laplacian, okay. So in fact, many more things can be said, like we can get a robust measure of the connectivity of the graph using lambda 2, something called Cheeger's constant. For the Cheeger's constant, it can give bounds for the Cheeger's constant using lambda 2, okay, both upper and lower bounds. Yes.
The same arguments, can you say number of components of G is multiplicity of 0 minus 1?
Number of components is multiplicity of
0 and then minus 1.
I think that should be true. So let me check. So in the connected case, what are you getting? So if the multiplicity of 0 is 1, then it has one component. The multiplicity of 0 is 2, then you will get two components. Multiplicity will tell you exactly how many components are there.
Yeah, that's what I want.
Without that minus 1.
Yes.
Okay, yeah. Okay. And I want to show you one of the important representation of this quadratic form associated with the Laplacian. Okay, so if I take any vector x in Rn, then this x transpose Lx, if you look at the quadratic form associated with this Laplacian, so this has a nice representation. So this can be written as sum of squares in this way. Okay, just take the difference of the entries of the vector which you are choosing. Okay, the difference is taken along the edges and square it. Okay, so in many of the applications, if you see wherever the Laplacian matrices are applied, most of the cases I have seen this expression is used. Okay, so today I will show you at least two applications of this type of expression. Okay, so let us give a proof of it. So for Laplacian, we have a formula in terms of Q of G. Just apply that. This is Q of G into Q of G transpose X. So what is X transpose Q of G? It's a vector. What are the entries of this vector? X transpose Q of G is a row vector. What are the entries? The first entry is you take the difference of the vector X, the entries of the vector X, okay, with respect to the edge, first edge. Okay, if Ij is the first edge, then in the first component you will get something like Xi minus Xj and so on, corresponding to every place. Okay, next we are taking the transpose of it. It is Xi minus Xj and so on. Just take the dot product of it, you are going to get Xi minus Xj the whole square. I just explained for the first row. It's okay, right? You okay with this? Okay. Now, we'll show that if the algebraic connectivity of the graph is high, then we'll show that the graph itself should be well connected. Okay, so by well connected, what we mean? So I think most of you know what is the definition of vertex connectivity. What's the definition of vertex connectivity? The minimum number of vertices you have to remove from the graph so that the resultant graph should be disconnected. If I start with a connected graph, okay, if it is not a connected graph, then the number of components after removing these vertices should increase. Okay, that's the definition of vertex connectivity. This algebraic connectivity gives a lower bound for the vertex connectivity. Okay, so let us define vertex connectivity. So this is the, I'll write down the minimum number of vertices to be removed from G. Okay, let us take a connected graph. So you can define for disconnected graphs too. Okay, such that removal of these vertices disconnects the graph. Okay.
So for complete graph, we have
What are you going to define? That I will discuss. What is the
trivial means no edge.
okay? So either disconnected graph or a single vertex. You want to say that or okay? So vertex connectivity of Kn is n minus 1. Okay. So examples. So it is denoted by alpha of G. Okay. So what is alpha of Kn? N minus 1. If I take like complete bipartite graph, minimum of
Keep it out because I use alpha for independence now.
oh okay. Okay, K I will use. Kappa in Bande and Murthy, what's the notation used? Okay, that alpha, beta, alpha for vertex connectivity, beta for edge connectivity. Okay. Oh, okay, kappa I will use. Okay. Then what about Cn? Cn is 2. Okay. Okay, and so on. So Fiedler proved that in 1960s. So he showed that the second smallest eigenvalue of the Laplacian gives a bound for this this quantity. Okay, this vertex connectivity. Okay, so let me state that. So maybe I'll prove a lemma first before giving the main theorem. Okay, so let G be a graph. And S be a subset of. Okay, then okay, define G minus S. How to define G minus S? So G minus S is the graph, is a subgraph obtained from G by deleting the vertices of S and the edges incident with S. Okay, you take a graph and you pick up a subset of vertices. Okay, by G minus S I mean remove all the vertices in S and then remove all the edges which are having n vertices in S. Okay, so we can compare the algebraic connectivity or the second smallest eigenvalue of these two graphs. Okay, so what's the connection? Then lambda 2 of G, okay, this should be less than or equal to, you look at the lambda 2 of G minus S, okay, plus the number of elements in S. Okay, by lambda 2 of G I mean lambda 2 of the Laplacian. Okay, we are dealing with only Laplacian eigenvalues. Lambda 2 of G is less than or equal to lambda 2 of G minus S plus the number of vertices in S. Okay, let me check the statement. Okay, that's it. Okay, the proof is a nice application of the sum of squares expression. Okay, we will do that. Okay, so maybe I will recall something about the variational characterizations. You can for lambda 2, you have a nice formula. This is minimum over x transpose Lx. Normalize it. Yeah, let me normalize it with the norm x is equal to 1. Okay, 2 norm equal to 1. Then it should be orthogonal to the eigenspace corresponding to the eigenvalue 1. Okay, so it should be orthogonal to then the all ones vector. Okay, the variational characterization you have seen, right? So lambda 2 is equal to minimum of, if you want to see a proof, maybe in the tutorial we can do that. Okay, so lambda 2 is given by this formula. Okay, okay, now let us start with let us take the vector, the eigenvector corresponding to the x. Okay, so let me start with let x be the eigenvector corresponding to the second smallest eigenvalue of g minus. Okay, I'm using y there. I will stick to y. Okay, I'm assuming this is normalized. That is 2 norm of 2 norm is same as inner product y with y. Y transpose y equal to 1, and y is orthogonal to all ones vector. Okay, now I'm going to use this vector to construct a vector x in Rn. Okay, so maybe I didn't use any numbers for it, any dimension I didn't mention anywhere. Okay, so now you define or it's better to mention that this lives in y lives in r power cardinality of g minus s. Okay, that is n minus cardinality of s. I'm going to define a vector x in r power n as follows. Okay, we'll construct a vector x using y. So what's the natural way? I want to keep this orthogonality and norm 1. We can just append zeros. Okay, so this is the way we are defining xi to be equal to, you keep yi if I is in S, 0 otherwise. Okay, then the 2 norm of x is same as the 2 norm of the vector y. This is equal to 1, and the inner product of x, y and x with the e is equal to 0. Okay, so I have a vector which is orthogonal to all ones vector, and it has norm equal to 1. Hence I can look at the variational characterization for the second smallest eigenvalue of g. Okay, so let us look at the second smallest eigenvalue of g. So lambda 2 of g is equal to minimum over some norm z is equal to 1. Z is perpendicular to all ones vector in Rn. Okay, into x transpose Lx. X transpose Lx is same as this we have already derived here. This is summation over I adjacent to j zi minus zj the whole square. So this quantity, so this x is a particular vector in this collection. So lambda 2 is less than or equal to summation I is adjacent to j xi minus xj the whole square. Okay, now what can you do? The part of this sum you can replace by this lambda 2 of g minus s, right? So we'll split the sum into two parts. So one part is corresponds to all the edges which are part of g minus s, and then whatever is left out. Okay, so maybe G minus S. Okay, let us give a notation for the H set. Let E prime equal to the H set of G minus S. Okay, so with this notation, this is same as the edge Ij belongs to E prime xi minus xj square plus summation belongs to E is the inset of the graph G, E minus E prime, xi minus xj square. Are we done? So this can be rewritten as in this way. This is same as, so this quantity is Ij in E prime, that means that both I and J are in G minus S. So this will be same as Y minus Y transpose Ly, that is same as lambda 2 of G minus S. Okay, so this quantity is same as lambda 2 of G minus S. The second term you can simplify in this way. So I belongs to S and summation I J E xi minus xj square. Then what about this quantity? I is in X, I is in S, J is in S complement. So if I is in S, then what is the value of Xi? Xi is Yi. What's the value of Xj? It is not in S, so that is 0. Just I'll get Xi square. So this is equal to, maybe here I can put a less than or equal to. Okay, just I'm considering only i's, maybe some edges may be there, both the ends are inside S complement itself. Some of the edges can be there, both the ends are inside the S complement itself. So you can keep a less than or equal to here, that will not affect our work. Plus summation I belongs to S, summation. Sorry? Because of some of the edges which may have both the ends in S itself. Okay, so those things also we are discarding there. That's why we need a inequality here. Okay, so this is Yj square. Okay, but Yj square has length equal to 1. We are taking only part of that vector y. So this will be less than or equal to 1. Okay, so this sum is less than or equal to 1. So this is less than or equal to lambda 2 of G minus S plus summation I in S. Okay.
So here, so
Yes.
xi should be yi if I is not S.
Sorry.
In the definition of xi, shouldn't be that y.
Yeah, you are right. It should be in
Yeah.
G minus S, the complement. Yeah, thanks. Yeah. So here it belongs to S. So I'm writing here Yj square. Yeah, correct. Okay. This is same as lambda 2 of G minus S is lambda 2 of G is less than or equal to lambda 2 of G minus S plus the number of elements in S. Okay. Are we done? From here, can we conclude that the algebraic connectivity should be less than, the lambda 2 should be less than or equal to the vertex connectivity? So if we take a set S whose removal disconnects the graph, so G minus S is a disconnected graph. If G minus S is disconnected, then what do you know? Lambda 2 should be equal to 0. Lambda 2 of G minus S is equal to 0. So if you substitute here, what you will get? Lambda 2 of G is less than or equal to lambda 2 of G minus S, that is 0, plus number of elements in S. S is the set whose removal disconnects your graph. So that shows that lambda 2 should be less than or equal to the vertex connectivity. Okay. So as a consequence of this, okay. So this says that lambda 2 of G is less than or equal to lambda 2 of G minus S. This thing. Okay. So as a consequence of this, if G is other than Kn, okay, complete graph on n vertices, then you have lambda 2 of G is less than or equal to the algebraic connectivity of G.
Interlacing property or curve.
Yeah, you don't need interlacing here.
We are considering only integer subgraph whenever we are removing S from G. So that the second smallest eigenvalue is always greater than or equal to. Yes, second smallest eigenvalue.
That's a good question. I think Sebi explained when he was doing. When you are considering a subgraph, and if you consider the Laplacian corresponding to the subgraph, that need not be a principal submatrix of the Laplacian of the original graph which you started. Degree may vary. Interlacing we can't apply in this state. Okay. Okay. Yes. When does equality holds? Do you have any characterization for equality?
I think you can calculate here. So when you go from when you have a little bit up, when you have the inequality, yeah. So if you see like in the sum above it, like where you put the 1, you can make it a little bit more precise, because so what you get for every so that one is, I think it should be J should be not in S, because so the
Okay.
yeah so it's something about J not in S. So when you do the calculation there, you basically, it's going to be lambda 2 of G minus S is clear, and then you're going to sum up for every J not in S, you will sum up Yj squared as many times as you have an edge from that J, an edge that goes into S, and that's going to be the degree of the number of neighbors of J intersect with S. So you write it like that, like a summation for all over J not in S of that, and then you can upper bound it by cardinality of S. So you can analyze. I think equality happens here. You have to have like some kind of all the edges in between or something like that.
Okay, this is an independent set setup.
Right?
Yes, you need to be independent set, or
I don't know if S has to be independent, because S is kind of. My impression is that you just need all the edges between S and G minus S.
okay. S may have some edges, but I don't know. Maybe we can discuss that in the tutorials. Okay, we'll see. Oh, join of two graphs.
Yeah, so that's
Okay,
exactly
yeah.
what it means. The S and everything else, you have all the edges between S and G minus S.
Okay. Is it the paper by Steve and Pati? Kirtland and Pati? Okay. I think there is a paper about it.
Yeah.
Steve Kirtland and Sukanta, they wrote. Yeah, Correct. Okay. So do you have any doubt on this part? I'm sorry about these notations. Yeah, this should be. So we are rewriting the edges which are not part of E prime, which are in E. Okay. So here when I write less than or equal to, so I'm going to skip some of the edges. So for that I wrote the inequality here, but here I should have mentioned J should not be in yes. Okay, that's okay. So this idea is very common, like so you just cleverly construct some vector and put it inside the quadratic form. Okay, that will help you in a lot of other instances. So I will tell you two more things. What I have. Okay, so define something called bisection problem. The problem here is you have to partition the vertex set into two parts, subject to some constraints. Okay, so our setup is G is a simple graph. And then if you give a partition, if it is given a vertex set by partition, say V equal to V1 union V2, define the boundary or denoted by this dou of V1 comma V2 is the set of all edges, okay, which are having Vi comma Vj such that Vi is in V1, Vj is in V2. Okay, so you have a graph G, you have V1 something like this, V2 something like this. You collect all the edges between the partition V1 and V2. Okay, so even though we write here bipartition, like it's not really a bipartition, like between the vertices of V1 you may have some edges. Okay, just we want to partition the vertex set into two parts such that we partition the vertex set into two parts and then collect all the edges which are passing from V1 to V2. Okay, so this is also called a cut. This is a cut. If you take uh, for some V1 subset of V, V1, V minus V1. This is called a cut. Okay, here we don't know, like V1 and V2 they may overlap. Okay, there may be some overlapping. So here if you consider V1 and the complement of V1, then we are going to call this this is cut associated with that vertex at V1. Okay, so bisection. So this is the definition of bisection. It's a bipartition of the vertex set of its vertex set. Okay, in which the number of vertices in the partition V1 and V2 they differ by one at most. Okay, in which number of vertices in the two parts are differ by at most one. So if number of elements in V, if number of elements in V is a even number, then it's like you can equally partition V1 and V2, V1 and V2 to have same number of elements. Suppose number of elements in V is odd, then we can't expect for a equal partition. So at most one difference is allowed. Okay. The problem is just only for even cardinality I will define. Let cardinality of V be even. Define B of G. Okay. This is called the smallest bisection. The smallest bisection of G. Okay, as follows: B of G is equal to minimum over all subsets of V with the cardinality of S is equal to cardinality of V minus S. Okay, just to minimize the number of edges between the set S to its complement. So definition clear, the smallest bisection of G denoted by B of G, that is given in this way. So you take a cut, okay, such that the vertex set associated with the cut has the property that number of elements in the set S is equal to the number of elements in its complement. Okay, so I'm assuming cardinality of V is even. You have to minimize this quantity. Okay, so you have to find out this number B of G. It's the problem. Huh?
In the definition of bisection, are the two parts allowed to intersect or not?
So S and V minus S. So here it is, when I'm defining this one, they can overlap, but here after this I'm not allowing to overlap.
No, this is just the smallest edge cut. No, but the parts are equal.
Constraint is the cardinality of S is equal to cardinality of V minus S.
So you want to split the vertices in half.
Yeah.
So if you don't have that restriction, is edge, this would be edge connectivity.
What's the complexity for edge connectivity? Computational complexity. Calculating that one.
I think it's
Efficiently, polynomial time. Okay. Okay. Then this problem is more interesting when you put one more constraint. This is an NP-hard problem. You don't have any easy algorithm to solve this problem. You will see a spectral bound for this quantity B of G. Okay. So you have to calculate this B of G. Okay. So this is one of the hard problems in computation. Okay, so we don't have any efficient algorithm to calculate this quantity B of G for all families of graphs. Okay, so this is a useful technique. Suppose if you can't calculate some quantity efficiently, then you go for some relaxation. Okay, or try to establish some bounds for it. Okay, so morning I think SEBI did one thing, the independence number. I think that's also NP-hard quantity to calculate. Okay, you can think of that's a bound for these things. Okay, and there is an interesting reason follow up for what SEBI did in the morning, that the bounds are not tight. Okay, they're far away from tight. So there is a paper which title itself, this inertia bounds are far away from tight. Okay, I think 2019 or 2020 it appeared in Journal of Algebraic Combinatorics. If you're interested, you can see that. Okay, so here like we are going to establish a spectral bound for this quantity B of G. Okay. Okay, so I am going to again do a trick. This is well known and useful in found in many of the applications. Okay, so given a cut or given this set S, let us associate a vector with it. Okay, a vector of size n. Okay, assume that the cardinality of V is n. So if you give a subset and then what is the natural vector one can define? The characteristic vector you can see. okay, with the plus 1 and minus 1. So let us define that vector, and that gives us something interesting. Okay, so let me take since we are taking minimum over a finite collection, this should be attained. Let us take S1 be the subset for which this minimum is attained. Okay, let us start with that. Let S1 be the or S1 be a optimal bisection. Okay, so if S1 be a an optimal bisection, so corresponding to this S1, define your vector. Define the vector x in Rn as follows. This is like the characteristic vector. Xi, define it to be equal to 1 if I is in S, and define it to be minus 1 if I is not in S. Sorry? Okay. I'm yet to state it. Yeah, correct. Then okay, so then what is x transpose x for this vector? What is x transpose x? No, it's not 0. The n, okay, cardinality of the vertex set, that is n. Now what is x transpose Lx? This is, we use the formula which we derived, okay, so that is xi minus xj the whole square. Now see the possibilities for xi minus xj. So xi and xj both are either, both of them are from the set plus minus 1, okay. So if xi and xj both of them are having same sign, then 0, okay. So in terms of the definition of the vector, you see, if xi and xj, if both of them are same sign, then both of them should be either in S or both of them should be in the S complement, okay. So this will be different from 0 only when xi is in S and I is in S and j is in S complement, or vice versa, okay. So that's going to give me 2 square, that is 4, which is same as 4 times the number of crossing edges, that is same as yeah. So with this observation, I can state the theorem. So theorem says that B of G, this quantity, is greater than or equal to n over 4 times lambda 2 of G. Okay, this lambda 2 of G is the second smallest eigenvalue of the Laplacian. What's the proof? So again, look at this formula. Lambda n is equal to minimum over that quantity. Okay, and maybe one more observation I can make here. The sum of the entries of this vector xi, that is 0, because cardinality of S is equal to cardinality of V minus S. So that is same as saying that this vector x is orthogonal to all ones vector. Now you can see the vector which we constructed here, that satisfies all the constraints, except this is not having norm equal to 1. Maybe you can normalize it by 1 by root and something. Okay, so lambda 2 of G, you have the formula minimum over it's equal to 1, or the other version I will use x different from 0 with x is perpendicular to E, x transpose Lx This is same as the same minimum summation xi minus xj the whole square divided by x transpose x. Okay, xi already used, we will use z. So this is so the minimum, this should be less than or equal to, what's the result? So this should be less than or equal to, if I replace the minimum, the collection by a particular vector x which satisfies this condition, and I'm going to get this is less than or equal to the numerator. Okay, I will write one more step. This is less than or equal to I addition to j xi minus xj whole square divided by x transpose x. So now you get the result. That is lambda 2 of g is less than or equal to, the numerator is 4 into x transpose x is n. Okay, I have taken it to be s1. So this implies for the cut for the cut s1 the minimum is attained. So that is same as b of g is greater than or equal to 4 by n, that is n by 4 into lambda 2 of g. Okay. It's a nice idea, good to know when you are doing Laplacians. And one more result related to max cut. So how many of you know max cut? Max cut. Okay, I'll recall. So max cut problem. So this says that g equal to v comma e. This is given to you. The problem is find a subset S of V such that the cut associated with the this S is maximum. Here we don't have any restriction on S. Cardinality of S and S complement can be anything. It's a kind of problem similar to bipartition. You are bipartitioning the vertex set into two parts, but you are not restricting that. Cardinalities are the same, and that is a minimization problem. This is maximization problem. Okay, so the number max cut is denoted by MC of G. Okay, the max cut in a graph G is denoted by MC of G. Is defined as follows. So MC of G is maximum of cuts with just AC subset of V. Again, this is an hard problem to solve. Okay, you don't have any easy algorithm to calculate this quantity for given arbitrary graph. Okay, so we will give a bound for this quantity in terms of the largest eigenvalue of the Laplacian matrix. Okay, it's a result by Mohr and Polyak. I'll give a proof of it. The idea is same, just we are going to associate a characteristic vector and we'll use that vector to establish the spectral bond. Okay. Okay, so theorem and then I'll write the proof. I forgot to write, so I can. Theorem. The max cut of the graph G is less than or equal to n over 4 times the largest eigenvalue of your Laplacian. Okay. So again we are taking the maximum over subsets of V. It's a finite collection. The maximum will be attained for a set. Okay, so let us start with the set. Let S be the set for which the maximum is attained. Let S be a subset of V such that the maximum is attained, such that MC of G is equal to cardinality of S comma S complement. Okay. So now define a vector x in Rn as follows. Just a characteristic vector, define xi to be 1 if I is in S and define it to be -1 if I is not in S. Okay. So you know the variational characterization. What is the formula for lambda n? The largest eigenvalue of the Laplacian. For any symmetric matrix, what is the formula? Take the take the maximum. Okay, so maximum over y different from 0 in Rn, y transpose Ly. Okay. So again I am going to replace this maximum by a particular vector, so I can put a greater than or equal to, this is x transpose Lgx by x transpose x. Okay, so that is same as, okay, I'll write one more step. This is Lgx divided by x transpose x. This quantity is, use the sum of squares expression, ij raised into j xi minus xj the whole square divided by, what is the quantity? That is n, right? Now what is the numerator? Xi minus xj, 4 times the size of the cut. Okay, this is 4 times the size of the cut, that is MC of G. So this is one way to formulate a combinatorial problem into a spectral graph theoretic problem and solve. There are many more techniques. Even one of the well-known approximation algorithm to calculate MC of G is due to Gomans and Williamson, that uses some semi-definite programming. Okay, which I'm not going to discuss. Okay, so the interesting thing is, I think that algorithm will give a solution. The correctness is up to 0. I think 878. Okay, and this established in 1990s. So far there is no improvement. I think if you can improve it, it's going to solve this GUS conjecture in something global something is there. Okay, so I can give you a reference where you can there is a readable introduction to all those things. Okay, so in fact the one of the authors Gomans and Williamson, David P. Williamson, so he offered a course on spectral graph theory. In his webpage you can find his lecture notes. He explained those things really nicely. So most of these things I have taken from that lecture notes. Okay, so okay, maybe just we have some time, we'll just discuss something about Laplacian matrices. Okay, so let us consider the complete graph. Okay, Kn. What are the Laplacian eigenvalues of the complete graph? So you know adjacency eigenvalues. Okay, if Kn is the complete graph, what is the adjacency spectrum? A of Kn is -1 with the multiplicity n minus 1 and n minus 1 with the multiplicity 1. Okay, and you know maybe first course in linear algebra you might have studied this result. If you have if you know eigenvalues of a matrix, let's say B, if you know all the eigenvalues of your matrix B, let's say lambda 1 to lambda n are the eigenvalues. Suppose if you want to calculate the eigenvalues of the matrix B plus AI, then what are the eigenvalues of this matrix? Lambda 1 plus A, lambda 2 plus A up to lambda n plus A. So if you use this result, you can get the Laplacian spectrum of Kn from adjacency spectrum of Kn. What's the connection here? L is given by D minus A, but D is n minus 1 times identity minus A. Okay, so this result says that n minus 1 minus the adjacency spectrum. So this is going to give me n with the multiplicity n minus 1, 0 with the multiplicity 1. Okay, so one interesting thing is the like the spectrum. If the spectrum of a graph is Laplacian spectrum or adjacency spectrum, okay, if it is given in this n with the multiplicity n minus 1, 0 with the multiplicity 1, okay, if you have any graph which have spectrum as this quantity, this set, then that should be complete graph. Okay, these type of graphs are called graphs determined by their spectrum. Okay, and this proof is not hard. Can you give me some suggestion? The proof is really simple. Maybe first time if you are seeing, maybe you have to work a bit. Sum of the eigenvalues is yes. Yeah, you can properly say that. So his argument is consider the Laplacian matrix, look at the diagonals. The diagonals gives you the degrees. Yes, you want to say something? That's for the eigen adjacency. Okay. Yeah, you can use that. You can prove via adjacency also. Okay. So his argument is take the trace. Trace gives you the sum of the vertex degrees. The first theorem of graph theory says that is equal to twice m. Okay, and that is for the complete graph you're going to get m into n minus 1 by 2. If you take any simple graph, if it has n into n minus 1 by 2 edges, then the graph should be a complete graph. Okay, so for complete graph it is really simple. Okay, the proof is the complete. So this gives the proof of the fact that complete graphs are determined by their spectrum. Okay, now one more question is, so we can show that the Laplacian eigenvalues of any graph, if you take the largest Laplacian eigenvalue should be less than or equal to n. Okay, so one question is, when n will be part of the Laplacian spectrum? Okay, so this says that if n is occurring as an eigenvalue with the multiplicity n minus 1, then complete graph is the only possibility. The question is, suppose just n, I don't know about multiplicity. With multiplicity at least one, n is part of the part of the Laplacian spectrum. Okay, then also we can say something about the graph. Okay, so that that I will prove in the afternoon. Okay, that maybe in a tutorial way we can develop the proof. Okay, you need to know of join and other things. Okay, is the problem clear? When n will be an eigenvalue of the Laplacian matrix. Okay, so we'll discuss that thing in the afternoon. And maybe we have 5 more minutes. I'll try to give one more result. If time permits, maybe Sebi will prove the matrix tree theorem. Okay, so that says that if you take the Laplacian matrix, okay, I'm going to prove a fact related to the matrix tree theorem. Okay, if you take the Laplacian matrix, suppose if you want to count the number of spanning trees in the graph, okay, then using the Laplacian matrix you can get a explicit formula for it. That's known as matrix tree theorem. So that says that you look at you pick any entry of the Laplacian arbitrarily. Okay, now look at the cofactor associated with that entry. Okay, or in other words, just close your eyes, pick any random entry, remove the row corresponding to the entry and column corresponding to the entry, calculate the determinant of that submatrix. Okay, in absolute value that is going to give you the number of spanning trees in the graph. Okay, so that one fact used in that in that proof of that result was this one. I'll just brief a proof of it. If you take any matrix X, if X is any matrix, a square matrix, okay, if X is any square matrix, with row sums and column sums are equal to 0. The row sums with row sums and column sums are equal to 0, then the determinant of any of the submatrices, okay, Xij, okay, this is the notation I'm using, submatrix obtained by deleting the ith row and jth column. Okay, then the determinants of all these matrices Xij's are the same. No matter whatever entry you are picking. Okay, so this can be thought of as I pick the entry Xij, then remove the row corresponding to that entry, that is the ith row, and remove the column corresponding to the entry jth column. Okay, so if you have a matrix X whose row sums and column sums are equal to 0, then the determinant of this submatrices are independent of the submatrix you are choosing. Okay, so Laplacian matrix satisfies this condition. Both the row sums and column sums are the same. Okay, so proof. So let us look at X 1, 2. Okay, now how does it look like? This is your X. Okay, we will start with X1, 1. So this is our X1, 1. Let us compare X11 and X12. Okay, so what is the difference in X11 and X12? Huh? So X11 is the matrix we obtained by removing the first column and first row. Okay, and X12 is the matrix obtained from X by removing the first column, sorry, the second column and first row. So what is the difference between x1? But only the first columns are different. Okay. Now look at the matrix x12. What can you say about this column? x12. Okay. So rest of the entries are the same for both the matrices. Okay. Can you compare this column x11 with this x12? That's the question. Okay. But we have both the row sums and column sums are equal to 0. Since the row sum is equal to 0, it implies that if you sum all the entries of this x12, the columns of x12, if you put it here, that should be negative of this column. Okay, because in x12 I'm summing everything. Okay, if I add the first column to it, I'm going to get 0 column, since the row sums are equal to 0. Hence, if I skip this first column, if I sum everything and if I put it in the first place in the x12, then that should be negative of this column. Okay, as we saw that the difference between x11 and x12 is only in the first column they differ. Okay, so the way, how do you get x12 from x11? Just replace the first column of x12 by x11. So you are replacing the negative of a column, negative of the column. Okay, hence the determinant will multiply by -1. And of course I claim the cofactor only. I'm claiming, oh sorry, the determinant, the cofactors. What is right? -1 power cofactor is better. Instead of giving my or -1 power I plus j, you can put into the determinant. Okay, this, they are the same, or that is the cofactors, the same for any ij. Okay, so this proof will be this result will be used in the proof of matrix tree theorem in one place. Okay, so I want to. Okay, in the afternoon we will see the proof of this thing with some more things. Okay, so I'll stop here. Any questions? Okay, then we'll go for lunch.
Notion of a quotient matrix for in that case. So I will tell you about Hammer's interlacing. So as before, we have a graph vertex set V and edge set E, and we have a partition of the vertex set into M subsets, non-empty subsets. So assume that this is a partition of V. So like I said before, this partition doesn't have to be equitable. To this partition, we associate a quotient matrix. The quotient matrix B, let's say Bij of this partition is an M by M matrix, is defined as follows. The entry Bij equals the number of edges between Vi and Vj divided by the cardinality of Vi for any I and j between 1 and m. So this is the average number of neighbors that the vertices in Vi have, that the neighbors live in Vj. Okay. So the theorem that we want to prove states the following. One, the eigenvalues of this quotient matrix B interlace the eigenvalues of A. Okay. And two, if the interlacing is tight, this is what we defined this morning, then the partition pi is equitable. Okay. All right. So we want we had I'm not going to write it again. The Courant-Hilbert theorem that we saw earlier this morning. We saw an application of Cauchy interlacing, and we'll see how Courant-Hilbert theorem will also be used here. So let me show you how that works. So as before, we will use this the matrix, the characteristic matrix of a partition, where the columns are all the characteristic vectors of V1, V2, Vn. Okay, so denote by P the n by m characteristic of the partition pi. So maybe let me do it here, like to help us understand. I'll illustrate how this works by a small example. Okay, so let's say my graph gamma let's say is the graph, this graph just k4 minus an edge, something like this. And I have 1, 2, 3, 4. Okay, and let's say my partition V1 is 1, 2, and my partition V2 is 3, 4. Just happens to be equal, but in general they don't have to have equal size. Okay. I'm not going to write the adjacency matrix of A. We'll talk about how you can get its eigenvalues in a little bit, but let's see B. What will be, so B will be indexed by V1, V2, V1, V2. And now again, in the entry, in the diagonal entry here, 1, 1 is going to be the average degree inside there, and it just happened, it's 1. Okay. In the entry 1, 2, like I said, V1 is the one on the top, V2 is the one on the bottom. In the entry 1, 2, again, the easiest way may be just to count the edges and divide. So you see there are 3 edges and you divide by 2, so you get 3 over 2. Okay? And something similar will happen here. If you look from here, if you look up, you will see 3 edges and 2 vertices. So here it just happens to be symmetric, but it doesn't have to be. So you get 1. Okay? So that's 1. Let me give you one more example. So this is, let's say, B1 with this partition. Let me give you an example just so that I convince you that it doesn't have to be symmetric. Let's take the same graph, but now this is my, let me call it W1, and this is my W2. So just the one vertex here and 3 vertices here. So this one, I will call it B2. Inside here, I have 0. Going this way, I see 2. Backwards, what's the entry? You have 2 edges, but you have 3 vertices here, so the average will be 2/3. And inside here, you see 2. Okay? So that's another quotient, maybe for a different partition. Okay? Okay. Okay, so this n by m, it's something tall like this, as we talked before, and each part corresponds to V1, Vm. They're the characteristic vectors of V1, V2, Vm. Okay? So as we talked before, the columns of this matrix P are orthogonal. Okay. Here, for example, the matrix P here, you're going to have 4 vertices and 1, 2, 3, 4, and this is V1, this is V2. So you have 1 and 2, so it's 1, 1, 0, 0, and then you have 0, 0, 1, 1. Here, the matrix here, let's say P2, you will have W1, W2, the same labeling 1, 2, 3, 4, you have 1, 0, 0, 0, 0, 1, 1. Okay, that's all. Okay, now, if you remember, in the proof of Courant-Hilbert theorem, there was this matrix S. So we're going to need to cook up a matrix S. Now, the matrix S, what property did it have? Columns were orthonormal. Here, the columns are orthogonal. So we're going to make something, we're going to normalize this. I mean, there's not much normalization we have to do because already the distinct columns are perpendicular to each other. So we just have to normalize each of the columns so that they they have length 1. So let me see how we do that. Okay, so first let's write this. We have that P transpose P. We've seen this, we've done this calculation a few times, is going to be the diagonal with the cardinality of V1, cardinality of Vm, the diagonal matrix where you have the cardinalities on the diagonal because the columns are orthogonal. And this will equal some matrix D, D square, where D is the diagonal matrix where you have the square roots of the cardinalities. Square root of cardinality of V1, square root of cardinality of Vn. Okay. Now this one, because the parts are non-empty, this will be invertible. You know this. And what we'll do is we normalize now the P and we say define R to be P times D inverse. So D inverse is going to be, instead of square root, you have 1 over square root. So just try to figure out your matrix multiplication in your heads. But essentially this this R, what it does, it normalizes each column. It's each column of P is normalized. And then what do we want to show about this R? So then R transpose R equals identity of M. So what number are we? Okay, well, we were 21, now we're 22. So exercise 22. So do this calculation. D minus 1, P transpose P, diagonal, they kill each other. Okay? Okay? All right. So now we got our matrix R. We have our matrix A. So we can just say by Courant-Hilbert theorem, the eigenvalues of R transpose AR interlace the eigenvalues of A. Now, these R transpose AR, we don't know what it is. I mean, you can calculate it, but I don't know if it will be B. Let's keep the B somewhere. So let me write here B. Okay. So the goal now is to somehow relate the matrix here with the matrix here. Okay. So this is, this falls into your lap because you have a partition. Okay. I have this big tool, big hammer, which is Courant-Hilbert theorem. Okay, I already have my adjacency matrix A. I have the partition. The partition gives me this matrix whose columns are orthogonal. But for Courant-Hilbert, I need a matrix whose columns are orthonormal. So you just do that, okay? You apply it, and you get R transpose AR interlace A. But now R transpose AR, it's a little bit, can try to figure out what it is, and you have to figure out what it is with respect to B. So the thing that we haven't done is to figure out what B is. So you remember we did some calculation, I think yesterday, we calculated something like P transpose AP for this characteristic matrix when we're doing like equitable stuff. So if you do that calculation, you will get a matrix is going to be M by M, where you're going to keep count the number of edges between the parts. But now my matrix B has the number of edges between the parts, but it's normalized by this. Okay? So what happens is that the matrix B will be something like P transpose P inverse. P transpose P will be this diagonal of the cardinalities of the set V. And when I do inverse, I just introduce this thing. So the matrix B will be P transpose P inverse times P transpose AP. Something like this. So this is the key. So on one hand, you have Courant-Hilbert theorem, R transpose AR with A. And now, somehow, what I want to get to, I want to relate B to this R transpose AR. And in order to relate B to this R transpose AR, first I need to get my hands on B, which is this. And then you can write it as if you want, D minus 2 P transpose AP. Because D, you see, P transpose P is D squared, you take the inverse is D to the minus 2. I know it's a lot. So, okay. So now let's rewrite R transpose AR a little bit. So R is PD minus 1. So you'll have PD minus 1 transpose A R, which is PD minus 1. Okay. On this side, you're going to leave it like this because it kind of looks like AP. You have AP here, so you leave it like that. Now, here it's a transpose. You take the transpose. Now, you're lucky here because D minus 1 is a diagonal matrix, so it's going to stay the same. So it's D minus 1, P transpose A, P, D minus 1. So it's not quite B, but it's almost. It's just like, what can I do? Maybe what can I do to B to make it into this? You see, they both have this part here, but it's just this D minus 1, like this R transpose AR has them on this side, the other one has it, you know, something like that. So let's do D times B times D inverse. So then we get D, we have the formula there, D minus 1 P transpose AP times D. No, this one is D, okay, I haven't, let me see, so I don't need to, yeah, D minus 2, I'm sorry, yeah, thank you. D minus 2 P, P, and I have a D minus 1 on this side. Yes, D minus 1 is D minus 1 P transpose AP, D minus 1, which is exactly this one. So dBD minus 1 will equal R transpose AR. So what can you say about, so B and this matrix are similar. So therefore B and R transpose AR are similar. So if they're similar, they have the same eigenvalues. And if the eigenvalues of this interlace the eigenvalues of A, the eigenvalues of B will interlace the eigenvalues of A because they're the same as that one. Okay. The second part. So this is the proof. So there are two main ingredients. One, you have to know this big canon, big hammer, the Courant-Hilbert theorem. So you have A, you want to find some smaller matrix that interlaces its eigenvalues. So you need to multiply, find some kind of orthonormal matrix, okay? From the partition matrix, you get an orthogonal matrix pretty much for free by these characteristic vectors. And you just normalize that matrix and kind of, you know, it works. So that's the idea. Okay. I will not give you the proof of the other part because we have some things to go through, but let me give you a quick application of this theorem. Okay. But I will use the second part about interlacing is tight and all that. I will use it when I have the equality case of this theorem. So let me give you this theorem. This is called Hofmann's Hofmann's ratio bound, Hofmann bound, ratio bound. There is like a whole book written about applying this bound to various graphs. You can find more. There's an article by Wilhelm Hemmers. I think you should be able to find it online about the history of this bound, the history about the Hofmann ratio bound. And this is a recent paper, Hofmann's ratio bound. Because throughout the years, this bound was been attributed to other people and so on. And, you know, Wilhelm Hemmers, he writes down all his recollections about it. So you'll get math with a little bit of history. So it's an interesting thing. Okay, so what is this bound? This is a bound for the independence number of a graph again. So let gamma be a k-regular graph with n vertices and eigenvalues. So these are the eigenvalues of the adjacency matrix. K is the largest one, greater or equal to lambda n. So lambda n is the smallest. Okay. Then the independence number of the graph, so this maximum number of vertices such that no two are adjacent, is bounded from above. So here again, I'll take k to be, this k is going to be greater or equal to 1, so that we avoid trivialities. So this will be less than or equal than n times minus lambda n divided by k minus lambda n. So you can kind of see why it's called a ratio bound, because you have a ratio here. Now, something that may trip you up a little bit is that you're seeing negatives things. So this independence number of the graph will be a positive number. It's the maximum number of vertices in an independent set. Now here, this graph, because k is greater or equal to 1, the graph has edges. And when you have edges, lambda 1 is positive, and therefore lambda n is negative. So minus n is actually positive. So if I want it to be less scary, I can do it like this. I can put absolute value of lambda n. So sometimes you will see like this. And again, at the bottom also, I can make it less scary. I can do plus this. And you can, if you do it like in this way, you can see that this number, this ratio, lambda, absolute value of lambda n divided by k plus absolute value of lambda n is strictly less than 1. So this gives you some upper bound less than the trivial bound of n. You know, you have this. Okay. Okay. So let me show you how to prove this. And so this is the first part. There is a second part about equality, but I will do it after I give you the proof. Okay? So as before, let's take let S be an independent set of size alpha of gamma. So you take an independent set. We did it before. We took S and largest independent set, one of them. When we applied Cauchy interlacing, we looked straight into the adjacency matrix and we saw this big block of 0, and we used Cauchy interlacing to say something about this parameter being bounded by number of non-negative, non-positive, or all that stuff. Okay. Now here we'll do something different. So let me show you the picture. What we'll do here. So what you have here, you have this set S, where there are no edges, and you'll have the rest of the world V minus. So these are the antisocial, okay, vertices. Nothing happens in between. And then this is the real world, okay? So now this suggests a kind of a partition into S and V minus S, okay? So that's what we're gonna do. We're gonna take this partition into two sets, S and V minus S. We'll calculate this quotient matrix. we'll calculate these eigenvalues. We're going to say, okay, Hamer's interlacing tells us that we have some kind of interlacing, and we'll try to see what happens. What does it mean? Okay. So that's what I will say. Consider the partition V equals S, V minus S. The quotient, so this is what we'll figure out first. The quotient matrix of this partition is the following. So I'll call it B. And before I'm trying to do any interlacing, obviously before I want to use any eigenvalues, I need to have a matrix. I need this matrix, this quotient matrix. So let's figure out what this is. First of all, how big is this matrix? 2 by 2. Okay, how hard can it be? So this is S, this is V minus S. So usually when I did it in the examples, I always started from here and so on. But I won't start from here. I'll start slightly off, because here's the thing. If I have a vertex here, my graph is K regular. This vertex doesn't want to talk with any of these vertices here. So where are all these vertices friends? They're going to be here. So which entry in this matrix is going to be K? 1, 2. And actually, I should have started here, because here I know what it is. What should be? 0. Very good. First row. Now, what comes after first row? Second row. Very good. Yeah. So we have to do. We have to go look what happens this way. But now here, this way, in the entry 2, 1, think about it in that form. Entry 2, 1 is the number of edges between the parts divided by the cardinality on this size. Can you tell me how many edges do you have between the parts? K times cardinality of S. So I will just shorten this thing to alpha. So I will have K alpha, because here I have alpha vertices. So cardinality of S is alpha. Everyone has K neighbors this way. So between here, I have K alpha edges. And now I have to divide by this size. How much is this size? N minus alpha. I'm almost done. What about the entry 2, 2? Here. Yeah, something like this. So you can, because you know that you're losing K alpha, you're losing this out, and the graph is K regular, the thing here will be actually K minus this value, minus K alpha divided by N minus alpha. Okay, let me do it separately, so that maybe. So let's do it separately, so that so this is S, this is V minus S. In between, I know I have K alpha, okay? What do I want to calculate? I want to calculate the average degree inside here. So if I have a vertex here, X, so the antisocial ones were here, this vertex X will have some neighbors inside here. Let me call it T of X. And we will have some neighbors outside, okay? Which is obviously the remaining, which is obviously K minus T of X, okay? So the entry in the position 2, 2, what is it in terms of this T of X? Yes, it's going to be the average here, so it will be the sum over all X in V minus S of T of X, divided by how many of them are there? N minus alpha, because we know how much. Now, when you sum this number, maybe I should have done it let me call this actually S of X, just for You know what it is, but I'll just call it S of x, okay? Each of these t of x plus S of x equals k. So I can write this as summation over all x in v minus s, k minus S of x. And now this will be split into two. It will be summation k for all v minus s. That will be k times n minus alpha divided by n minus alpha. And then all these minus will be minus summation over all x in v minus s of S of x divided by n minus alpha. So here, this is k minus, here this is n minus alpha. But now, when you sum over all these vertices here, when you sum all their neighbors that live in here, what do you get? You just get the number of edges in between, which you know what it is. It's k alpha. Okay? So this is something standard whenever whenever you sum up the degrees in some induced subgraph, you have to take care of what happens the leftover. Like there's something that there will be some edges going out and so on that you have to be careful. Okay, so that takes care of the matrix. Yes.
For the matrix B, the row sum should and
Very good. So this will always happen. So if you have a k regular graph, and you take any quotient matrix that you want, and you define the entries of the quotient matrix the way we did, the row sums will always be k. The row sums will always be k. Okay. So now, okay, your colleague is helping us here. Row sums are k, so therefore lambda 1 of b is k. So we won't get much information out of that. But what is lambda 2 of b? Which is the same thing. In this case, you see, in this case, the m that we use in our proof of interlacing is 2. So this is the same thing as lambda m of b. And this will be how much? Minus. It's minus k alpha and minus alpha. So it's a negative. There's not much I can do with this. Lambda 1 is k. Well, you can apply everything you want. It's not going to help you anything. But the other thing helps me, okay? The other value. So by Hammer's interlacing, and what you use Hammer's interlacing, you use the one on the n side of it. So you look at this lambda 2 as being the smallest eigenvalue of this small matrix. So what will happen is that this smallest eigenvalue of B is going to be greater or equal than lambda n of A, which I call lambda. So it's the kind of the other type of inequality that's in the interlacing, okay? So the big matrix gets to lose this time to the small matrix, okay? So now let's write down what this means. Therefore, minus k alpha n minus alpha is greater or equal than lambda n. And now you just have to, what is our object of interest? Which number we want to go after? Alpha. So we have to do something here and just make sure you don't change sign, you make mistakes. So here, n minus alpha is positive, so I can move it there. So I will have minus k alpha greater or equal to n lambda n minus alpha lambda n. And you have to remember, so I just cross multiply. N minus alpha went here, n lambda n minus alpha lambda n. Now, I need alpha on one side, so I will move the k alpha here. I will move the n alpha here. So I will get minus n alpha, which is n times minus n lambda n, which is n like this, greater or equal than k alpha minus alpha lambda n. And we're almost there. You write this as alpha times k minus lambda n. k minus lambda n is positive, so you divide by it, so you get n minus lambda n, k minus lambda n, greater or equal to. Okay. So it's the simplest partition that you can think into two parts, independent set, and you can do something more general. You can apply it not just to independent sets. This will give you information about the average degree inside a set of vertices, if you want, in terms of the number of vertices and the eigenvalues. Okay. All right. So let me give you some examples where you can apply this, because we've done like some small example of eigenvalues. That's what I'll use for this part. Let me see what I can erase. I'll erase here. So yesterday I showed you how with the Peterson graph you have here the eigenvalues are what? 3, 1, minus 2. 3 has multiplicity 1. 1 has multiplicity, well, I don't know. I haven't proved that, but I'll do that. Okay, so we just showed that the eigenvalues are 3, 1, and minus 2. Okay, so this is my k. This is my lambda 10, because n is 10 here, the smallest. So you just apply it here. So you say alpha of Peterson, let's call it that, is less than or equal than, you first rewrite this, n minus lambda n, k minus lambda n, and then you write it's 10 times, this will be 2, k is 3 minus minus 2. So you get 20 over 5 is 4. Okay? So it's at most 4. Yesterday I showed you an independent set of size 3, but you can see here that I can pick a different one here. I have 4 vertices. This is independent set, and this is maximum because I'm guaranteed that there's nothing bigger. I mean, for Peterson graph, you can try to do it by hand. You can do it, but I just wanted to show you this. Okay. Maybe I'll do it now since we're at the Peterson graph. Let's quickly do the other bound to see the Kvetovich bound, the one about inertia. Let's try to do that as well. But for that one, I need to know the multiplicities of these eigenvalues, because I need to know how many, I have 3, 1, and minus 2, but I don't know how many 1s I have, and I don't know how many 2s. So let me call this multiplicity f, and this multiplicity g, and this one I know because the graph is connected, the multiplicity is 1. So if I want to find f and g, f plus g equals 9, because 1 plus f plus g should be 10, because that's, yeah. And where else do I find one more equation about f and g? We've done it before. We've looked at it. The trace. So you can look at the trace. So the trace of the adjacency matrix is 0, but it will be the sum of the eigenvalues. 3 comes with multiplicity 1, so 3 times 1, plus 1 times f, plus minus 2 times g. Okay, so I get that f minus 2g equals minus 3. And if you subtract from the first equation, you subtract the second equation, you get 3g equals 12. So this will be 4, and this will be 5. So g will be 4, f will be 5, and g will be 4. Okay? So now, if you apply the inertia bound, the one that we did this morning, at most, minimum. So first, let's figure out what the numbers are. N is 10. What's a n plus, and what is n minus? What's the number of positive eigenvalues? What's the number of negative? 6 and 10. 6 and 4, sorry, 6 and 4. And then this one is the maximum of the differences, so the minimum. So the minimum will be the minimum of 10 minus 6, 10 minus 4, which is 4. So in this case, it works both ways. Okay. Now there are many graphs on which these bounds get equality, but obviously they're not. There are also many graphs on which they don't give you what you want. One thing I will tell you here is what happens if you have equality, because that's important. So equality happens here if and only if this partition that you have here is equitable. This partition S V minus S is equitable. And there is another characterization of equality, which I won't give you here, in which it tells you that equality happens if and only if a vector which is related to the characteristic vector of S belongs to the eigenspace of lambda n. And that's what is used also in characterizing equality for this inequality in many situations. Okay, so in general, applying this bound, it will be like kind of somewhat the easier part. The harder part will be in the equality case when you want to analyze what happens if you have equality. Okay, so you can play with this if you have graphs, regular graphs. But the other thing is this is for regular graphs, and you can try to play with for some graphs. Whenever you're looking for independence number, you can get something like this. Okay. Let me tell you one more thing about this, and then I'll give you a proof of. Yes, question.
Which partition?
The partition. So the partition into any independent set of maximum size, and the rest will always be equitable. Okay. Yeah. Okay. What was I saying? What do I need to give? I wanted to do something before.
That's what he said.
Eh?
That is what he said. We are going to proceed.
Yes, but I forgot what I. Oh yes. So let me tell you one more thing about this. So also a consequence of this theorem, so corollary, if gamma is k regular, then I haven't defined this, but I'll define chi of gamma, which is a chromatic number of gamma, is going to be greater or equal than 1 plus k divided by absolute value of lambda n, where chi of gamma is the chromatic number. So chi of gamma, so it's the, okay, in case not everybody knows, so chi of gamma is the minimum, I don't know, let's call it t, such that we can partition, there is a partition of V into t parts, V1 blah blah Vt. Vt, such that all these parts are antisocial. So all these parts are independent sets, such that V1, Vt are independent sets. So you can have edges between the parts, but you cannot have any edges inside. It's equivalently, it's the minimum number of colors that you can color the vertices of the graph such that any two adjacent vertices get different colors. So here, the vertices here in V1 will get the same color, and there's no problem. So color classes are usually independent sets, are always independent sets. So, yeah. And so when you have this when you have, let's say T, if T is the chromatic number of gamma, the number of vertices in gamma n is cardinality of V. It's the sum of all I1 to T of cardinality of VI. Each of VI is independent set, so its cardinality is going to be less than this alpha of gamma. So what you get here is T times alpha of gamma, which is the chromatic number of gamma times alpha of gamma. So if you write it in terms of chi of gamma, you get that chi of gamma is greater or equal than n divided by alpha of gamma. So if you use, this is a combinatorial inequality, if you use this inequality with this inequality, it gives you this bound. That's all. So, okay. There's something more general here for this problem for graphs that are not necessarily regular, but I'm not going to do that right now. Okay. 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 So I plan to do something else for the remaining part of the. So how much time do I have? 20 minutes? 10 minutes? 15 minutes. So I will, I will be nice and not ask you to erase the board for a change. So yeah, you're welcome. And then so take this time to catch your breath, get some water, and then I'll tell you something else about matrix 3 theorem, which is about Laplacian matrix that Professor Kanan talked about. So. Okay, so I'll change gear and I'll talk about something else. As before, we have gamma VE. So let me give you some quick definitions. What is a spanning subgraph of gamma? A spanning subgraph of gamma is obviously a subgraph of gamma, but it is the one in which you keep all the vertices. So you just delete some edges. So it's a subgraph of gamma whose vertex set is V. And then second, what is a spanning tree of gamma? Well, surprise, surprise, it's a spanning subgraph that is a tree. That's all it is. Okay, so we have this example that we carried with us, the bow tie, friendship graphs. I don't know if the labeling is the same. We have this, okay? So now what we're interested in this parameter tau of gamma, which is the number of spanning trees of gamma. So here my graph is labeled, so I'm looking to count all the labeled spanning trees. Some of them may be isomorphic, but as unlabeled things, but I don't care. So for something like this, I keep the vertices, and what do I need to do? I need to destroy the cycles, and so you can see this is a spanning tree, but there are more. Okay, there are more spanning trees and so on. How many do you have in total? I'll give you like 10 minutes. No, we don't have 10 minutes. So, okay. So this is the theorem in. So let me write down the Laplacian matrix here. The Laplacian matrix here, we have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1 has degree 2, 2 has degree 2, 3 has degree 4, and then 2 and 2. And then 1 is adjacent to 2, so minus 1, minus 1, 0, 0. Oh, sorry. 1 is adjacent to 3. Thank you. Oh, thank you. Yes, you're right. Okay, here I have again this, and here I have minus 1, minus 1, minus 1, minus 1, minus 1. Okay, so what you do, you pick your favorite or your least favorite row, least favorite column. Okay, let's say they're the same. First and first, okay, because you want to destroy things early. Delete this. You get a 4 by 4 matrix here, which I call L11. Take the determinant, and that's your answer. Isn't that like magic? What kind of sorcery is this, you know? So this is what people call Kirchhoff matrix tree theorem. And there are many versions of it. The one that I'll give you is just this, that tau of gamma is the determinant of L, and I'll just put here x, x. So by this, I mean is the matrix L without row x and column x. How can it be? Okay, so we'll do it in a few steps. So earlier, Professor Kanan introduced the incidence matrix. I forget it was Q transpose or Q transpose Q? Q transpose. Okay, now you need some properties about this matrix Q. So one property of the matrix Q is every square submatrix of Q has determinant 0, -1, or 1. Very convenient, okay? Let me do the matrix here. So the way I will I'll do the orientation, I'll orient from smallest number to bigger number. So I don't need to do the arrows, so I'll just do the edges. So I have here 1, 2, 3, 4, 5. And here I'll do the edges lexicographically, 1, 2, 1, 3, 2, 3, 3, 4, 3, 5. And the first one I get a plus, the second one I get a minus. So which one? 4, 5. Thank you. So 1, 2, 1, -1, 0, 0, 0. 1, 0, -1, 0, 0, 0, 0, 1, -1, 0, 0. You can do it in how many ways? How many incidence matrices you have once you fix the labeling here and the labeling here? You just have to pick an orientation on each edge. So it's 2 to the power the number of edges. So, okay, so I'll just give you 1 here. Okay, so to prove that every square submatrix has determinant 0, 1, or -1, you use induction on the size of the matrix. If the submatrix is 1 by 1, I can prove it, because the matrix is 0, 1, -1. So that's clear, okay? Now, if we do the induction step, assume that we have some submatrix, and let's see what happens. So let's see we're lucky and we pick this submatrix. If we have like columns or a row of 0, if we have a column of 0, then we're happy because determinant is 0. What happens if we have something like here where every column has 2 non-zero entries? We're also happy or we're sad? We're happy because this is, you know, the rows are not are linearly dependent, so the determinant here is also 0. because 1 minus 1 minus 1 1 1 minus 1, so that's it. So therefore the only case that remains, if we have one row, let me see if I can find something like here. If we have one column in which we have exactly one non-zero entry, that non-zero entry, what has to be? 1 or minus 1. So if you expand according to that column, you're getting a 1 plus a smaller determinant, but your smaller determinant is 1 minus 1 is 0, so you're done. Okay? So this is very useful. Now, here, this is for connected graphs, so remember that the rank of Q is n minus 1. Professor Kanan proved this. Now, the third thing is, I erase my, let me do it here. So this matrix is what I call a fat matrix, because you have more columns than you have, in general, than you have rows. So here you have n vertices. Here you're going to, let me pick a set F, cardinality of F, n minus 1 of edges. I pick n minus 1 edges. So I get this weird matrix that is going to be tall, like n vertices, n rows, n minus 1 column. I claim that if I delete any row, this matrix here is invertible. Okay, why is that? So let's say first I don't delete this row. Here I have, well, it's invertible. No. Invertible, no wonder that you look funny at me. If and only if the graph with V and F is a spanning tree. So that's how the spanning tree come into play. They start playing. So first, let's say we have all the vertices. Here, let's say we have F, all the edges, okay? If this is a spanning tree, then this is an incidence matrix for that spanning tree, because I have all the vertices and I just have the edges. But the spanning tree is connected, so what should be the rank of it? N minus 1. Now the rows of this matrix, they add up to 0 all the time. So any subset of n minus 1 rows will be a basis. So if you delete one row, the remaining ones are linearly independent, so you're done. Okay? So that's the argument here. And so invertible will also mean that the determinant of such matrix will be what? Plus or minus 1. Okay? So then what the third ingredient is some big hammer, which is sometimes called Binet-Cauchy, sometimes called Cauchy-Binet. It may be called something else. So if you take this determinant of Lxx, which is going to be the determinant of this Q matrix in which you do something with X and you do something with X, like you delete the row X from Q and the column X from Q transpose, and it's going to be a summation of some kind of determinants of such matrices from here square for all F in F of cardinality n minus 1. So what will you pick up in this sum? For every F that is a spanning tree, you will pick up a determinant that is minus 1 or 1, but somehow you're lucky that it's squared, so you pick up a 1 and you get your answer. So that's kind of the proof of Kirchhoff matrix D theorem in 15 minutes, 10 minutes or something like that. So this is the proof that is given in Biggs' book, algebraic graph theory. And I'll send you, in a day or two, I will send you some write-up in which I'll give you the write-up of this, which you can read at length, not in like 10 or 15 minutes like we're doing now. Okay, so I'll stop here now. Thank you.
Say about the bijective proofs, the difficulty of counting the spanning
Okay, so now let us see about the graphs which are having n as a Laplacian eigenvalue. Okay, so morning we have seen that spectrum of the Laplacian spectrum of the complete graph is n with the multiplicity n minus 1 and 0 with the multiplicity 1, right? But we have seen that complete graph is the only graph which has this as a Laplacian spectrum. Okay, the question was, if I have a graph for which n is just an eigenvalue, can you say something about that graph? Okay, so we'll see a complete characterization of those type of graphs. Okay, we need some tools. Like this may be applied to some other problems also. We'll rigorously develop everything. Okay, the first one result about symmetric matrices. If you have if A and B are symmetric matrices, let A and B both are real symmetric matrices. Symmetric matrices, and B is positive semi-definite. B is PST. Then we can compare the eigenvalues of A and A plus B. Okay. In general, if you have two matrices A and B, we don't have any meaningful relation between sums and the individual individual eigenvalues of the individual matrices. Okay, so if A is symmetric and B is symmetric and positive semi-definite, then we have this relation. Lambda I of A is less than or equal to lambda I of A plus B. This holds true for every I equal to 1 to n. Okay, so yeah. So I'm not going to give a proof of it. The proof is similar to the characterization, variational characterization, the proofs we have seen many times. Like we have to cleverly construct a vector which is sitting inside in intersection of two subspaces. Okay, just you can take this as an exercise. You read the proofs of the variational characterization for eigenvalues. Okay, so the same technique will work here. Okay, we try to prove it. So we will use this theorem to prove our results. So one immediate consequence of this result is, if I have a spanning subgraph of a graph G, okay, G be a graph and H be a subgraph. Okay, so if H is just a subgraph, then we don't know any relation between or we don't have interlacing sort of thing between the Laplacian matrices, the Laplacian eigenvalues of G and Laplacian eigenvalues of H. If it is spanning subgraph, okay, then we have a relation. We can just apply this theorem there. Okay, so then the ith eigenvalue of the subgraph H should be less than or equal to the ith eigenvalue of the graph G. This holds true for all I equal to 1 to n. Okay, for arbitrary subgraphs, we don't have any interlacing type of things. Okay, if it is a spanning subgraph, then we do have this result. Okay. So how to show that? The proof is simple.
Eigenvalues of the adjacency or
Laplacian. So today, whole day I'm talking about only Laplacian. Okay, so lambda 1 less than or equal to lambda 2 eigenvalues of L of G. Yes. If it is just a subgraph, the Laplacian corresponding to the subgraph need not be the principal submatrix of the Laplacian of the supergraph. Degrees may vary, right? The subgraph degree will differ, the supergraph degrees may different. If it is a spanning subgraph, you will see it need not be a submatrix, but it will differ by a positive semi-definite matrix. Yeah, we will discuss that. Okay, so let us see what first we will prove it and then we will come to that point. So let us take H be a spanning H is a spanning subgraph. H1 let us define be a spanning subgraph. Spanning subgraph of G such that, so it's a spanning subgraph, so vertex set of H1 is vertex set of G, the edge set of H1 is, you take the edge set of G and then just remove the edges of H. Okay. Then what about Laplacian? L of H1 equal to, L of G equal to L of H1, L of H plus L of H1. Okay. So H1 is a subgraph, so H1 is positive semi-definite, hence you have this relation. Okay. So by the previous theorem, we have lambda I of G is less than or equal to lambda I of lambda I of H is less than or equal to lambda I of G for all I equal to 1 to n. Okay, so what is your question?
Not for any subgraph. Say that if it is any subgraph, then it can.
Yeah, so that you can append zeros and then you can apply this result for that. Okay, the interlacing result, whatever Sebi was proving in the morning, so that there you need a principal submatrix. So in general, when you take the Laplacian of a subgraph, the Laplacian need not be a principal submatrix of the Laplacian of the original graph. Okay, so in that aspect, suppose if you see, you give me, so that's also induced subgraphs, not any subgraph. Okay.
Here spanning subgraph, it could contain isolated vertices.
Yes. And here this is also, this need not be induced also.
Yeah.
Okay, when you are doing isolated vertices and all. Yeah, then for any subgraph we can apply this with isolated vertices. Then for Laplacian, in a sense, it's much stronger than what we had for adjacency case. Right. Yeah, good. So let us use this result to show the Laplacian eigenvalue of any graph is less than or equal to n. Okay, that's kind of trivial. Why it's the case? Yeah, complete graph has the largest eigenvalue of lambda n of kn is equal to n. Therefore, lambda n of any graph G on n vertices should be less than or equal to n, because kn can be written as, you take G plus G complement, then you can write down or G, the decomposition whatever we did. Okay, G and the G1 you define, so it will cover the entire kn. This is less than or equal to n. Okay. Now the main result is when the largest eigenvalue, largest Laplacian eigenvalue is equal to n. Okay, so let's prove that. We need the concept of join. The join of two graphs G and H This is denoted by edge is obtained by adding all possible edges from G to H. Okay, from every vertex of G, draw edge to every vertex of G to every vertex of H. Draw all possible edges. Okay, is obtained by adding edges between G and H such that every vertex in G is adjacent to every vertex in H. Okay, so let us see an example. So you take G to be something like this and H to be some triangle. Then what is join of G and H? Just a small example, okay. Something like this. Okay. The result says that so the main result which I am going to discuss says that the largest eigenvalue of a graph G is equal to n if and only if the graph G is a join of two graphs. Okay, that's what we are going to prove. So before that, if G and H are graphs, if you know all the Laplacian eigenvalues of G and H, then we can derive or we can get a formula for all the Laplacian eigenvalues of G join H. Okay, so that I will prove the formula first. So let us take G1 and G2 be graphs on n1 and n2 vertices, okay, respectively. So if the eigenvalues of G1 are the eigenvalues of G1, okay, of L of G1, let's say these are all 0 is equal to lambda 1 less than or equal to lambda 2 less than or equal to lambda n1, and the eigenvalues of L of G1, G2 are 0 which is equal to mu1 less than or equal to mu2 less than or equal to mu n2. If you have the complete information about the eigenvalues of the individual graph, then the eigenvalues of the join, the eigenvalues of the Laplacian matrix of the join is given by, so 0 should be there irrespective of whatever graph you are taking. 0 is part of the spectrum always, and then n2 plus lambda 2, n2 plus lambda 3, n2 plus lambda n, n1 plus mu 2, n1 plus mu 3, n1 plus mu n, and then n1 plus n2. Okay, so we have n1 plus n2 eigenvalues. Everything is covered here. Proof. 0 is an eigenvalue because we take all ones vector, that is done. For the rest of them we have to see. Okay. Just you have to cleverly like give the labeling for the vertices. Okay, so let us choose the labeling for the vertices in this way. Okay, the way is first keep all the vertices of G1 first. Okay, and then keep all the vertices of G2. Okay, so in this notation, can we fill this? Laplacian of G, this is equal to Laplacian of G1 plus how many vertices, how many edges we added? N2. So from here to, so this side we have N2, this side we have N1. So in this part we are adding N2 edges. So N2 times identity. Then minus J. Okay, because between any two vertices of G1 and G2 you have edge. Okay, and symmetrically fill here, this is minus J, and this part L of G2 plus N1 times identity. Okay, with this proper labeling we are getting in the nice format. Okay, so now let us look into so this is again a nice guess. You take the vector y to be equal to n2 times I n1 minus n1 times I n2. Okay, so block vector n2 times I n1, not I n1, I want to see E n1 or 1 n1 using this notation for it is a column vector whose all entries are equal to 1 of size n1. Okay, so this is the column vector of size n2 with all ones. Okay, so this is basically first n1 places I am keeping n2, the remaining places we are keeping minus n1. Okay, so for this vector let us see what's happening. So LG of y minus, okay, L of G1 plus N2 times identity minus J L of G2 plus N1 times identity. So we are going to do the block multiplication. This is N2 times all ones of size N1 minus N1 times all ones of size N2. Do the multiplication, what are you getting? L of G1 into N2 1n, that is 0, because row sum of L of G1 is 0, hence the first part vanishes. What about the second part? We are getting n square into n square into, we are multiplying with the identity, so it will stay as it is. Sorry, n2 square into all ones vector of size n1, then what you will get? n1 into n2. So this is plus n1 into n2 into all ones vectors of size n2. What about the next row? n1 plus n2, yes, n1 plus n2. Okay, yeah. Here number of rows is n1, so this is n1 by n2. Okay, yeah, you're right. Correct. So this is n1. Yeah, right. Otherwise, sum is not compactable. Yeah. So what about the next term? This is minus n2 into n1 1 n2 minus n1 square into 1 n2. So let us take an n2 common. So the first term. So this is n2 into n1 plus n1 plus n2 into sorry. Okay, n1 plus n2 into 1 n1 From here, let us take a n1 common out. Are we done? That is nothing but negative of, not negative, this is same as n1 plus n2 into n2 1 n1 n. That's the eigen equation. Okay. So we have seen 0 is an eigenvalue and n1 plus n2 is an eigenvalue. Okay. So far we didn't use any of the eigen equations corresponding to L of G1 and L of G2. If you use that, we will get rest of them. Okay. The crucial fact is, if you take any eigenvector corresponding to the non-zero eigenvalues starting from lambda 2, they are all perpendicular to all ones vector. J has all ones. If you multiply J with that eigenvectors, you are going to get 0. Okay. So let us do that. So this is one part. So if we take xi is an eigenvector of L1 corresponding to the eigenvalue lambda corresponding to lambda I. Okay, let's say for 2 less than or equal to I less than or equal to n, then you define yi equal to xi and zeros. You add n2 number of zeros with it. Okay. So xi is the eigenvector of L1 corresponding to the eigenvalue lambda I. Now from that xi we are constructing a vector yi, okay, by appending just n2 zeros. Okay. So now let us see whether it satisfies the eigen equation or not. Minus I minus j L of G2 plus n1 times identity. This is say 0. What do you get? So first entry LG1 xi, that is just lambda I, n2i, that is n2. Okay. So this is same as n2 plus lambda I xi. Second entry is j multiplied with xi. Xi is the eigenvector corresponding to non-zero or second corresponding to the rest of the eigenvalues other than lambda 1. Hence is orthogonal to all ones vector. So this will give me 0. Xi is different from 0. Hence this is an eigenvector corresponding to the eigenvalue n2 plus lambda 1, lambda i's. Okay. Then you can guess what are the rest of the eigenvalues by guessing the eigenvectors. Swap the role of, like, replace the role of xi by yi's. So here 0 and then keep yi's here. If you take yi's to be not yi's, maybe some zi's you take. Zi's to be the eigenvectors of this matrix L of G2 corresponding to the eigenvalues mu2 to mu n2. Then you are going to get rest of them. Okay. This gives a complete description of all the eigen. Okay. So whenever performing operations on two different graphs, it's always good to identify a proper labeling. Okay. If you can identify a proper labeling corresponding to the labeling, if the matrix has some nice structure, it will be easy to handle. Okay. For joins, like this is useful. This one. Yes, Sabi. So the students argued that if I take any subgraph, which is if not even a spanning subgraph, then I can append isolated vertices and the still results holds true. That means that this interlacing holds true for one side of the interlacing holds true for any subgraph for Laplacian.
Yes, sorry, yeah, something. But it's special for the Laplacian. You don't get anything.
Yeah, for the adjacency matrix. Yeah. And again, the other side you can't argue, right? Only the half of the interlacing holds true. Yeah, that's true. Up to that part is fine. Yeah. Good. Okay, good.
They're saying if and only.
No, I'm saying only one side. If and only if I don't know. What about the converse? What do you define converse? It's only one side I'm stating. Okay. Okay, so let us state the main result. Theorem. Let G be a graph on n vertices. Then let G be a graph on n vertices. Then n is an eigenvalue of the Laplacian L of G if and only if G is join of two graphs. G is the join of two graphs. Okay. One side of the result is already proved. Can you say which direction we proved already? If G is join of two graphs, then n is an eigenvalue. That's follows from here directly. Okay. So proof: if n is a if G is a join of two graphs, then n is an eigenvalue of Laplacian of G. Okay, that follows from here. That theorem, okay, the theorem which we proved. Okay, so to prove the other direction, let us take G is not a suppose that, okay, maybe let us assume n is an eigenvalue of G, n is an eigenvalue of L of G. Okay, suppose that G is not a join of two graphs. G is not a join of two graphs. So now consider this non-negative matrix L plus J. Okay, this is a non-negative matrix. Right, so the Laplacian only the now negative entries were in the off diagonal. Now we have added this J, so everything is non-negative now. Also note that this L plus J into E. E stands for the all ones vector. Can you evaluate this?
Diagonal of every entry.
LE equal to 0. LE all ones vector. Okay, this is just n times E. So n is an eigenvalue of this matrix. Okay, so n is an eigenvalue of L plus J. Okay, so since G is not a join of two graphs, Okay, so we cannot write this L plus J as the following form. Okay, we cannot write L plus J the block form something like this. Okay. Oops. Or L cannot be written in this way. Okay, that means that if you consider this matrix L plus J, this is irreducible. So irreducible, like if you don't know what is irreducible, just draw a graph associated with this matrix L plus J, okay, as follows. The vertices of just the rows of this matrix or columns of this matrix, and you are going to keep an edge between two vertices I and J only when the corresponding entry is different from 0. Okay, so we have seen this notion for 0 1 matrices, okay, that can be extended for arbitrary non-negative matrices. Okay, so L plus J, this is a matrix of size n. You draw a graph of size graph with n vertices. Okay, so you keep an edge between the vertices I and j only when this L plus J ijth entry is different from 0. Okay, so and the Paran-Frobenius whatever we discussed for 0 1 adjacency matrices, okay, that holds true for arbitrary irreducible non-negative matrices. That says that the largest eigenvalue of L plus J is simple. Okay. Can you complete the proof? So by Paran-Frobenius, the largest eigenvalue of L plus J is simple. And what are the eigenvalues of L plus J? The eigenvalues of L plus J are so lambda 2 to lambda n and then n. We know lambda n is less than or equal to n for everything. Okay, that means that n has multiplicity equal to 1. So lambda n should be strictly less than n. Okay, so that is lambda n strictly less than n. But we started with the assumption that n is an eigenvalue of L of G. Okay, so lambda 2 to lambda n are the possible non-zero eigenvalues. Okay, when the largest eigenvalue is strictly less than n, hence the eigenvalue n cannot be an eigenvalue for L of G. Okay, so this completes the proof of fact that n is an eigenvalue of the Laplacian if and only if it is join of two graphs.
If G is not a joint, then we cannot write L equal to this. Where is this?
If you can't write down in this way, then when you are adding j to it, if you can write in this way, what is the meaning? L plus j will be L1 0 0 L2 2. So that is reducible. If you cannot write down in this form, then it is irreducible. Okay.
So why are the eigenvalues of L plus J lambda 2?
You can calculate it. So j advantage is like if you hit with any of the eigenvector other than the eigenvector corresponding to 0, everything it will vanish. So L plus j of, you take any eigenvalue u orthogonal to eigenvector, it's the same as Lu, the same as lambda I into u. So u2 to un it will be preserved. Lambda 2 to lambda n with the same eigenvector. Okay. The only left out thing is that n. I will do that. Maybe after that we will try to connect it. Okay. Yeah. So in adjacency matrices, like if you know the spectrum of the graph, then you can't say much about the spectrum of its complement. Okay. But in the Laplacian case, we can say something. Okay. In fact, say everything. Let us see what. So if lambda is an eigenvalue of let's say L of G, okay. Okay, so maybe let us observe something first. So what is L of G plus L of G complement? It's same as n minus 1 identity minus j yeah, this is the one, right? Okay. One is captured here also. Ni minus j. So L of G is equal to n minus j minus L of G complement. So if lambda is an eigenvalue of L of G, let us take this different from 0, then if L of this, let's say lambda u, sorry, so this implies n I minus j minus L of G complement times u, this is equal to Lg of u, which is equal to lambda u. So this is just nu minus, so I have taken the eigenvalue other than 0 or starting from the second smallest eigenvalue. So ju is 0. So here this is just L of G complement to u. This is equal to lambda u. Okay. So L of G complement of u, this is equal to n minus lambda into. So if the spectrum of L of G is the spectrum of L of G is 0 lambda 2 to lambda n, then what is the spectrum of L of G complement? 0 n minus lambda 2 n minus lambda n. Okay, so if you know the Laplacian spectrum of a graph, then you know the complement of it. Okay, so SEBI suggested a problem. You can calculate the eigenvalues of complete bipartite graph using.
For this one, you can also
Okay.
using this thing. So I think if you have n is an eigenvalue of Lg, by this, like if n is an eigenvalue of Lg, so your lambda n is going to be n or something, yeah, one of those. Then the spectrum of the complement of G will contain two zeros. And because it contains two zeros, the graph is going to be disconnected. So the complement of it is going to be disconnected. And if the complement is disconnected, then G itself is going to be a joint of those
two parts.
Yeah. So that's kind of
that gives another proof for that.
So this is an easy tool if you want to calculate. If you have graphs and you don't know how to calculate, you can think about this. Replace your graph by the complement and see if the complement is easy to calculate. Then you can play with this game. Like for example, like complete bipartite. Like you can give them the complete bipartite graph. And you don't know, but if you say the complement of the complete bipartite, you have two disjoint cliques. So you have the eigenvalues, and then you get the complement values. It's just a nice trick.
Yeah. Okay. Okay, so maybe I will just state the statement of matrix Forest theorem. I think some of you are asking for general subset itself. Okay, I'll state the matrix Forest theorem. From there you can see. I'm not going to prove, as I said. So this says that so let G be a graph and the vertex set of G is equal to 1 to n. You take any subset, okay, any proper subset, non-empty proper subset of the vertices, okay. Now you look at the determinant of so this notation, this open bracket W by W stands for you remove the rows and columns corresponding to the indices of W, okay, from the Laplacian matrix. You take the Laplacian matrix, from the Laplacian matrix, remove the rows and columns corresponding to the index set W. The matrix tree theorem, we took W to be a singleton set, okay, removed one row and one column. So here we are removing this. Okay, so this quantity, this is equal to, okay, the number of spanning forest with the cardinality of W components okay. If you take W to be singleton, you have a forest with only one component, okay. So here you have a forest with the cardinality of W, spanning forest with the cardinality of W components. So with one more thing, every component of the spanning forest contains exactly one vertex of W. Okay, so every component contains one vertex of W. Okay, this is the general matrix Forest theorem. Okay, so maybe one more interesting consequence of matrix tree theorem, whatever proof Sebi gave. So you can give a spectral formula for the number of spanning tree. So morning we saw the formula. What was the formula? Determinant of, so matrix tree theorem says that this tau of G, the number of spanning trees is equal to determinant of, sorry, determinant of, you take LIA. Okay. So this quantity, indeed, this is same as you take all the eigenvalues starting from 2 to n. Okay, 2 to n, just take the product of them, divide by n, you will get the number of spanning trees. It's a proper spectral formula, you can say. Okay. So how to prove, any idea? Sorry? Yes, coefficient of x in the characteristic polynomial. Okay, so if you remember the first lecture I said something about the coefficients of the characteristic polynomial, they are nothing but sum of the principal minors of order n minus 1 by n minus 1. Okay, so how many principal minors we have? N principal minors. Okay, and the other way to look at the same coefficient is sum of the products of the eigenvalues taken n minus 1 at a time. Okay, So lambda 1 equal to 0 for every graph. Okay. So if you have to avoid lambda 1, then we have only one product, that is lambda 2 to lambda n. So lambda 2 to lambda n is equal to n times the number of spanning trees. So hence the number of spanning trees is equal to the product divided by n. Okay. You want to add anything? Laplacian amount. Anything we missed? Okay. Then we'll stop here. Okay. Can stop.